Chapter 9. Integrated Circuits. Objectives. 1. Understand integrated circuit scaling issues. 2. Describe complementary metal oxide semiconductor process integration. 3. Understand the basics of logic gates and charge-coupled devices. 4. Study the operation of different memory cells: static random access memories, dynamic random access memories, flash. 5. Understand integrated circuit packaging. Just as the transistor revolutionized electronics by offering more flexibility, convenience, and reliability than the vacuum tube, the integrated circuit enables new applications for electronics that were not possible with discrete devices. Integration allows complex circuits consisting of millions of transistors, diodes, resistors, and capacitors to be included in a chip of semiconductor. This means that sophisticated circuitry can be miniaturized for use in space vehicles, in large-scale computers, and in other applications where a large collection of discrete components would be impractical. In addition to offering the advantages of miniaturization, the simultaneous fabrication of many integrated circuits on a single silicon wafer greatly reduces the cost and increases the reliability of each of the finished circuits. Certainly, discrete components have played an important role in the development of electronic circuits. However, most circuits are now fabricated on the silicon chip rather than with a collection of individual components. Therefore, the traditional distinctions between the roles of circuit and system designers do not apply to integrated circuit development. In this chapter we shall discuss various types of integrated circuits and the fabrication steps used in their production. We shall investigate techniques for building large numbers of transistors, capacitors, and resistors on a single chip of silicon, as well as the interconnection, contacting, and packaging of these circuits in usable form. All the processing techniques discussed here are very basic and general. There would be no purpose in attempting a comprehensive review of all the subtleties of device fabrication in a book of this type. In fact, the only way to keep up with such an expanding field is to study the current literature. Many good reviews are suggested in the reading list at the end of this chapter. More important, current issues of those periodicals cited can be consulted for up-to-date information regarding integrated circuit technology. Having the background of this chapter, one should be able to read the current literature and thereby keep abreast of the present trends in this very important field of electronics. In this section we provide an overview of the nature of integrated circuits and the motivation for using them. It is important to realize the reasons, both technical and economic, for the dramatic rise of integrated circuits to their present role in electronics. We shall discuss several main types of integrated circuits and point out some of the applications of each. More specific fabrication techniques will be presented in later sections. Advantages of integration. It might appear that building complicated circuits, involving many interconnected components on a single silicon substrate, would be risky both technically and economically. In fact, however, modern techniques allow this to be done reliably and relatively inexpensively. In most cases an entire circuit on a silicon chip can be produced much more inexpensively and with greater reliability than a similar circuit built up from individual components. The basic reason is that many identical circuits can be built simultaneously on a single silicon wafer, Fig 9.1. This process is called batch fabrication. Although the processing steps for the wafer are complex and expensive, the large number of resulting integrated circuits makes the ultimate cost of each fairly low. Furthermore, the processing steps are essentially the same for a circuit containing millions of transistors as for a simpler circuit. This drives the integrated circuit industry to build increasingly complex circuits and systems on each chip, and use larger silicon wafers, for example, 12-inch diameter. As a result, the number of components in each circuit increases without a proportional increase in the ultimate cost of the system. The implications of this principle are tremendous for circuit designers. It greatly increases the flexibility of design criteria. Unlike circuits with individual transistors and other components wired together or placed on a circuit board, Integrated circuits allow many extra components to be included without greatly raising the cost of the final product. Reliability is also improved since all devices and interconnections are made on a single rigid substrate, greatly minimizing failures due to the soldered interconnections of discrete component circuits. The advantages of integrated circuits in terms of miniaturization are obvious. Since many circuit functions can be packed into a small space, complex electronic equipment can be employed in many applications where weight and space are critical, such as in aircraft or space vehicles. In large-scale computers it is now possible not only to reduce the size of the overall unit but also to facilitate maintenance by allowing for the replacement of entire circuits quickly and easily. Applications of integrated circuits are pervasive in such consumer products as watches, calculators, automobiles, telephones, television, and appliances. Figure 9:1 a 300 mm diameter, about 12-inch, wafer of integrated circuits. The circuits are tested on the wafer and then sawed apart into individual chips for mounting into packages. Photograph courtesy of Texas Instruments. Miniaturization and the cost reduction provided by integrated circuits mean that we all have increasingly more sophisticated electronics at our disposal. Some of the most important advantages of miniaturization pertain to response time and the speed of signal transfer between circuits. For example, in high-frequency circuits it is necessary to keep the separation of various components small to reduce time delay of signals. Similarly, in very high-speed computers it is important that the various logic and information storage circuits be placed close together. Since electrical signals are ultimately limited by the speed of light, about 1 foot per nanosecond, physical separation of the circuits can be an important limitation. As we shall see in section 9.5, large-scale integration, LSI, of many circuits on a silicon chip has led to major reductions in computer size, thereby tremendously increasing speed and function density. In addition to decreasing the signal transfer time, integration can reduce parasitic capacitance and inductance between circuits. Reduction of these parasitics can provide significant improvement in the operating speed of the system. We have discussed several advantages of reducing the size of each unit in the batch fabrication process, such as miniaturization, high frequency and switching speed improvements, and cost reduction due to the large number of circuits fabricated on a single wafer. Another important advantage has to do with the percentage of usable devices, often called the yield, which results from batch fabrication. Faulty devices usually occur because of some defect in the silicon wafer or in the fabrication steps. Defects in the silicon can occur because of lattice imperfections and strains introduced in the crystal growth, cutting, and handling of the wafers. Usually such defects are extremely small, but their presence can ruin devices built on or around them. Reducing the size of each device greatly increases the chance for a given device to be free of such defects. The same is true for fabrication defects, such as the presence of a dust particle on a photolithographic mask. For example, a lattice defect or dust particle 1/2 micrometer in diameter can easily ruin a circuit which includes the damaged area. If a fairly large circuit is built around the defect it will be faulty. However, if the device size is reduced so that 4 circuits occupy the same area on the wafer, chances are good that only the one containing the defect will be faulty and the other 3 will be good. Therefore, the percentage yield of usable circuits increases over a certain range of decreasing chip area. There is an optimum area for each circuit, above which defects are needlessly included and below which the elements are spaced too closely for reliable fabrication. Types of integrated circuits. There are several ways of categorizing integrated circuits as to their use and method of fabrication. The most common categories are linear or digital, according to application, and monolithic or hybrid, according to fabrication. A linear integrated circuit is an integrated circuit that performs amplification or other essentially linear operations on signals. Examples of linear circuits are simple amplifiers, operational amplifiers, and analog communications circuits. Digital circuits involve logic and memory, for applications in computers, calculators, microprocessors, and the like. By far the greatest volume of integrated circuits has been in the digital field, since large numbers of such circuits are required. Because digital circuits generally require only the on-off operation of transistors, the design requirements for integrated digital circuits are often less stringent than for linear circuits. Although transistors can be fabricated as easily in an integrated form as in a discrete form, passive elements, resistors and capacitors, are usually more difficult to produce to close tolerances in integrated circuits. Integrated circuits that are included entirely on a single chip of semiconductor, usually silicon, are called monolithic circuits, Fig 9.1. The word monolithic literally means one stone and implies that the entire circuit is contained in a single piece of semiconductor. Any additions to the semiconductor sample, such as insulating layers and metallization patterns, are intimately bonded to the surface of the chip. A hybrid circuit may contain one or more monolithic circuits or individual transistors bonded to an insulating substrate with resistors, capacitors, or other circuit elements, together with appropriate interconnections. Monolithic circuits have the advantage that all of their components are contained in a single rigid structure that can be batch fabricated, that is, hundreds of identical circuits can be built simultaneously on a SI wafer. On the other hand, hybrid circuits offer excellent isolation between components and allow the use of more precise resistors and capacitors. Furthermore, hybrid circuits are often less expensive to build in small numbers. The integrated circuit was invented in February 1959 by Jack Kilby of Texas Instruments. The planar version of the integrated circuit was developed independently by Robert Noyce at Fairchild in July 1959. Since then, the evolution of this technology has been extremely fast-paced. One way to gauge the progress of the field is to look at the complexity of integrated circuits as a function of time. Fig 9.2 shows the number of transistors used in metal oxide semiconductor microprocessor integrated circuit chips as a function of time. It is amazing that on this semi-log plot, where we have plotted the log of the component count as a function of time, we get a straight line over 4 decades, indicating that there has been an exponential growth in the complexity of chips. The component count has roughly doubled every 18 months, as was noted early on by Gordon Moore of Intel Corporation. This regular doubling has become known as Moore's Law. The history of integrated circuits can be described in terms of different eras, depending on the component count. Small-scale integration refers to the integration of 1 to 100 devices, medium-scale integration to the integration of 100 to 1000 devices, LSI to the integration of 1000 to 100,000 devices, very large-scale integration to the integration of 100,000 to 1 million devices, and now ultra-large-scale integration, ULSI, to the integration of 1 million to 1 trillion devices. Of course, these boundaries are somewhat fuzzy. The next generation has been dubbed gigascale integration. WAGs have suggested that after that we will have RLSI, or ridiculously large-scale integration. The main factor that has enabled this increase in complexity is the ability to shrink or scale devices. Typical dimensions or feature sizes of state-of-the-art dynamic random access memories, DRAMs, at different times are also shown as a semi-log plot in Fig 9.3. Once again, we see a straight line, reflecting an exponential decrease in the typical feature sizes with time over 4 decades. Clearly, one can pack a larger number of components with greater functionality on an integrated circuit if they are smaller. As discussed in section 6.5.9, scaling also has other advantages in terms of faster integrated circuits which consume less power. While scaling represents an opportunity, it also presents tremendous technological challenges. The most notable among these challenges lie in lithography and etching, as discussed in section 5.1. However, since scaling of horizontal dimensions also requires scaling of vertical geometries, as discussed in section 6.5.9, there are also tremendous challenges in terms of doping, gate dielectrics, and metallization. In addition, small features and large chips require device fabrication in extremely clean environments. Particles that may not have caused yield problems in a 1 micrometer integrated circuit technology can have catastrophic effects for a 22 nanometers process, which requires purer chemicals, cleaner equipment, and more stringent clean rooms. Figure 9.2 Moore's law for integrated circuits, exponential increase in transistor count as a function of time for different generations of microprocessors. The dashed line indicates projections based on the International Technology Roadmap for Semiconductors, ITRS. Notice that the transistor count in the future may not increase at the same rate as in the past, due to practical constraints such as economics and power dissipation. Figure 9.3 Exponential decrease in typical feature size with time for different generations of dynamic random access memories, 16 kilobytes to 32 gigabyte dynamic random access memories. For reference, sizes of blood cells, bacteria, and viruses are shown on the micrometer scale. Dimensions below 100 nanometers are considered to be in the realm of nanotechnology. In fact, the levels of cleanliness required bypass the best surgical operating rooms early in the evolution shown in Fig 9.3. The cleanliness of these facilities is designated by the class of the clean room. For instance, a Class 1 clean room, which was state-of-the-art in 2000, has less than one particle of size 0.2 micrometers or larger per cubic foot. There are more of the smaller particles and fewer of the larger ones. Obviously, the lower the class of a clean room, the better it is. A Class 1 clean room is much cleaner than a Class 100 fabrication facility, or fab. As one might expect, such high levels of cleanliness come with a hefty price tag. A state-of-the-art fab in 2014 comes equipped with a price tag of about $5–10 billion. In spite of the costs, the economic payoff for ULSI is tremendous. Just for calibration, let us examine some economic statistics at the dawn of the third millennium. The total annual economic output of all the countries in the world, or the so-called gross world product, GWP, is about 85 trillion US dollars. The US gross national product is about $16 trillion, or about a fifth of the GWP. The worldwide integrated circuit industry output is about $350 billion, and that of the entire worldwide electronics industry in which these integrated circuits participate is about $2 trillion. As a single industry, electronics is one of the biggest in terms of the dollar amount. It has surpassed, for example, automobiles, worldwide sales of about 50 million cars annually, and petrochemicals. About 1 billion smartphones are sold annually worldwide. Perhaps even more dramatic than these raw economic numbers is the growth rate of these markets. If one were to plot integrated circuit sales as a function of time, one again finds a more or less exponential increase in sales with time over 3 decades. Of great importance to the consumer, the cost per electronic function has dropped dramatically over the same period. For example, the cost per bit of semiconductor memory, dynamic random access memory, has dropped from about 1 cent per bit in 1970 to about 10 to 5 cents per bit today, an improvement of 5 orders of magnitude in 45 years. There are no parallels in any other industry for this consistent improvement in functionality with such a lowered cost. Although integrated circuits started with bipolar processes in the 1960s, they were gradually supplanted by MOS and then by CMOS devices, for reasons discussed in chapters 6 and 7. Currently, about 90% of the integrated circuit market is metal oxide semiconductor based and about 8% bipolar junction transistor based. Optoelectronic devices based on compound semiconductors are still a relatively small component of the semiconductor market, about 4%, but are expected to grow in the future. Of the metal oxide semiconductor integrated circuits, the bulk are digital integrated circuits. Of the entire semiconductor industry, only about 14 are analog integrated circuits. Semiconductor memories such as dynamic random access memories, serial random access memories, and non-volatile flash memories make up approximately 25% of the market, microprocessors about 25%, and other application-specific integrated circuits, ASICs, about 20%. Now we shall consider the various elements that make up an integrated circuit, and some of the steps in their fabrication. The basic elements are fairly easy to name: transistors, resistors, capacitors, and some form of interconnection. There are some elements in integrated circuits, however, which do not have simple counterparts in discrete devices. We shall consider one of these, charge transfer devices, in section 9.4. Discussion of fabrication technology is difficult in a book of this type, since device fabrication engineers seem to make changes faster than typesetters do. Since this important and fascinating field is changing so rapidly, the reader should obtain a basic understanding of device design and processing from this discussion and then search out new innovations in the current literature. Complementary metal oxide semiconductor process integration. A particularly useful device for digital applications is a combination of N-channel and P-channel metal oxide semiconductor transistors on adjacent regions of the chip. This complementary metal oxide semiconductor, commonly called complementary metal oxide semiconductor, combination is illustrated in the basic inverter circuit of Fig 9.4a. In this circuit the drains of the two transistors are connected together and form the output, while the input terminal is the common connection to the transistor gates. The P-channel device has a negative threshold voltage, and the N-channel transistor has a positive threshold voltage. Therefore, a zero voltage input, VEN equals 0, gives zero gate voltage for the N-channel device, but the voltage between the gate and source of the P-channel device is VDD. Thus the P-channel device is on, the N-channel device is off, and the full voltage VDD is measured. At Vout, i.e., VDD appears across the non-conducting N-channel transistor. Alternatively, a positive value of VEN turns the N-channel transistor on, and the P-channel off. The output voltage measured across the on N-channel device is essentially zero. Thus, the circuit operates as an inverter with a binary 1 at the input. The output is in the zero state, whereas a zero input produces a 1 output. The beauty of this circuit is that one of the devices is turned off for either condition. Since the devices are connected in series, no drain current flows, except for a small charging current during the switching process from one state to the other. Since the complementary metal oxide semiconductor inverter uses ultra little power, it is particularly useful in applications such as electronic watch circuits that depend on very low power consumption. Complementary metal oxide semiconductor is also advantageous in ultra-large-scale integrated circuits, section 9.5, since even small power dissipation in each transistor becomes a problem when millions of them are integrated on a chip. Figure 9.4 Complementary metal oxide semiconductor structure, A. Complementary metal oxide semiconductor inverter, B. Formation of P-channel and N-channel devices together. The device technology for achieving complementary metal oxide semiconductor circuits consists mainly in arranging for both N and P-channel devices with similar threshold voltages on the same chip. To achieve this goal, a diffusion or implantation must be performed in certain areas to obtain N and P regions for the fabrication of each type of device. These regions are called tubs, tanks, or wells, Fig 9.5. The critical parameter of the tub is its net doping concentration, which must be closely controlled by ion implantation. With the tub in place, source and drain implants are performed to make the N-channel and P-channel transistors. Matching of the two transistors is achieved by control of the surface doping in the tub and by threshold adjustment of both transistors by ion implantation. Including bipolar transistors in the basic complementary metal oxide semiconductor technology allows flexibility in circuit design, particularly for providing drive currents. The combination of bipolar and complementary metal oxide semiconductor, called BiCMOS, provides circuits with increased speed. Attention must be paid in CMOS designs to the fact that combining N-channel and P-channel devices in proximity can lead to inadvertent, parasitic, bipolar structures. In fact, a PN-PN structure can be found in Fig 9.4b, which can serve as an inefficient but troublesome thyristor, see Chapter 10. Under certain biasing conditions, the PNP part of the structure can supply base current to the NPN structure, causing a large current to flow. This process, called latch-up, can be a serious problem in CMOS circuits. Several methods have been used to eliminate the latch-up problem, including using both N-type and P-type tubs, separated by trench isolation, Fig 9.6. The use of two separate tubs, wells, also allows independent control of threshold voltages in both types of transistor. We can illustrate most of the common fabrication steps for MOS integrated circuits by studying the flow of a twin-well self-aligned silicide. Salicide, CMOS process. This process is particularly important because most high-performance digital integrated circuits, including microprocessors, memories and application-specific integrated circuits, ASICs, are made basically in this way. In order to make enhancement mode N-channel devices, we need a P-type substrate, and vice versa. Since complementary metal oxide semiconductor requires both, we must start either with an N-type or a P-type wafer and then make selected regions of the substrate have opposite doping by forming wells. For example, Fig 9.5 shows a lightly doped P epitaxial layer on a P+ substrate. We can make N-channel devices in this layer. By implanting N-wells wherever needed, we can make P-channel devices also. This is an N-well complementary metal oxide semiconductor process. Alternatively, if we start with an N substrate and make P-wells in certain regions, we have a P-well complementary metal oxide semiconductor process. For optimal device performance, however, it is usually desirable to separately implant both the N and the P-well regions, which is called twin-well complementary metal oxide semiconductor. The rationale for this can be appreciated if we keep in mind that for a state-of-the-art integrated circuit, typical doping levels are 1,000 quadrillions of atoms per cubic centimeter and junction depths are around 1 micrometer in these wells. Figure 9.5 Self-aligned twin-well process, A. An N-well formation using P-donor implant and a photoresist mask, B. P-well formation using B-acceptor implant. A thick, 200 nanometers, tank oxide layer is grown wherever the silicon nitride oxide stack is etched off, and the tank oxide is used to block the B implant in the N-wells in a self-aligned manner. C. An isolation pattern for field transistors showing a B-channel stop implant using a photoresist mask. D. Local oxidation of silicon wherever the nitride mask is removed, leading to thick Locos field oxide. Figure 9.6 Trench isolation. A trench or groove is etched in the substrate with the use of reactive ion etching and is refilled with oxide and polysilicon. Trench isolation provides superior electrical isolation compared with Locos, and uses less silicon real estate. Photograph courtesy by Tom Way IMD/BTV copyright 1998 IBM. The doping levels have to be high enough to prevent punch-through breakdown due to drain-induced barrier lowering, DIBL, in the metal oxide semiconductor field effect transistors, but low enough to keep the threshold voltages acceptably small. If we choose to use the P substrate for N-channel devices as in Fig 9.5a, the P-type epitaxial layer must be doped to 1,000 quadrillions per cubic centimeter, and the implanted N-type layer must be achieved by counterdoping at a level of 2,000 quadrillions per cubic centimeter, resulting in a net N-type doping of 1,000 quadrillions per cubic centimeter, but a total doping in this region of 3,000 quadrillions per cubic centimeter. Such high levels of total doping are detrimental to carrier transport because they cause excessive ionized impurity scattering. Hence, for high-performance integrated circuits, the starting epitaxial doping level is generally very low, 10 quadrillions of atoms per cubic centimeter. This layer is grown on a heavily doped substrate, 10,000 quadrillions of atoms per cubic centimeter, to provide a highly conducting electrical ground plane. This helps with noise problems in integrated circuits and helps minimize the problem of latch-up by bypassing majority carriers, in this case holes, to the P+ substrate. To form the twin wells in a self-aligned fashion, we first grow thermally a pad oxide, 20 nanometers, on the silicon substrate, followed by low-pressure chemical vapor deposition, LPCVD, of silicon nitride, 20 nanometers. As shown in Fig 9.5a, this oxide nitride stack is covered by photoresist, and a window is opened for the N-well. Reactive ion etching, RE, is then used to etch the oxide nitride stack. Using the photoresist as an implant mask, we then do an N-type implant using phosphorus. Phosphor is preferred to arsine for this purpose because phosphor is lighter and has a higher projected range. Also, phosphor diffuses faster. This fast diffusion is needed to drive the dopants fairly deep into the substrate to form the N-well. After the implant, the photoresist is removed, and the patterned wafer is subjected to wet oxidation to grow a tank oxide, 200 nanometers. Note in Fig 9.5b that the tank oxidation process consumes silicon from the substrate, and the resulting oxide swells up. In fact, for every micron of thermally grown oxide, the oxidation consumes 0.44 micrometers of silicon, resulting in a 2.2-fold volume expansion. The oxide does not grow in the regions that are protected by silicon nitride, because nitride blocks the diffusion of oxygen and water molecules, and thereby prevents oxidation of the silicon substrate. The pad oxide that is used under the nitride has two roles. It minimizes the thermal expansion mismatch and concomitant stress between silicon nitride and the substrate. It also prevents chemical bonding of the silicon nitride to the silicon substrate. Using the tank oxide as a self-aligned implant mask, i.e., without actually having to do a separate photolithographic step, one does a P-type well implant using boron, B, Fig 9.5b. The tank oxide must thus be much thicker than the projected range of the B. The concept of self-alignment is very important and is a recurring theme in integrated circuit processing. It is simpler and cheaper to use self-alignment than a separate lithographic step. It also allows a tighter packing density of the twin wells, because it is not required to account for lithographic misalignment during layout. The phosphor and the boron are then diffused into the substrate to a well depth of typically a micron by a drive-in diffusion at very high temperatures, 1000 degrees Celsius, for several hours. After this diffusion, the silicon nitride oxide stack and the tank oxide are etched away. Since the tank oxidation consumes silicon from the substrate, etching it off leads to a step in the silicon substrate delineating the N-well and P-well regions. The step is important in terms of the alignment of subsequent reticles and is shown in an exaggerated fashion in Fig 9.5c. The step, however, is disadvantageous from the depth of focus point of view during lithography. So, instead of a self-aligned twin well process as just described, one often uses two separate lithography steps for the two well implants. This approach leads to a more planar structure, but a slightly larger well geometry because the wells are not self-aligned. There are many other variations of CMOS processes used, depending on the application. Next, we form the isolation regions or the field transistors that guarantee that there will be no electrical crosstalk between adjacent transistors, unless they are intentionally interconnected, Fig 9.5c. This is achieved by ensuring that the threshold voltage of any parasitic transistor that may form in the isolation regions is much higher than the power supply voltage on the chip, so that the parasitic channel can never turn on under operating conditions. From the threshold voltage expression EQ 638, we notice that threshold voltage can be raised by increasing substrate doping and increasing gate oxide thickness. However, a problem with that approach is the subthreshold slope SEQ 666, which degrades with increasing substrate doping and gate oxide thickness. One needs to optimize both threshold voltage and S such that the off-state leakage current in the field between transistors is sufficiently low at zero gate bias. A stack of silicon dioxide silicon nitride is photolithographically patterned as in Fig 9.5c and subjected to reactive ion etching. A boron channel stop implant between the twin wells increases the acceptor doping and thus increases the threshold voltage in the P well between the N-channel transistors, the field threshold. However, B will compensate the donor doping on the N-well side, and thus reduce the threshold in the N-well between P-channel devices. The B-channel stop dose must thus be optimized to have acceptably high field thresholds in both types of wells. After the channel stop implant, the photoresist is removed and the wafer with the patterned nitride oxide stack shown in Fig 9.5c, without photoresist, is subjected to wet oxidation to selectively grow a field oxide 300 nanometers thick. The nitride layer blocks oxidation of the silicon substrate in the regions where we plan to make the transistors. This procedure, where silicon is oxidized to form silicon dioxide in regions not protected by nitride, is called local oxidation of silicon, LOCOS, section 6.4.1. In this case, LOCOS provides electrical isolation between the two transistors, as shown in Fig 9.5d. The volume expansion of 2.2* upon oxidation is an important issue because the selective oxidation occurs in narrow, confined regions. The compressive stress, if excessive, can cause dislocation defects in the substrate. Another issue is the lateral oxidation near the nitride mask edges, which causes the nitride mask to lift up near the edges, forming what is known as a bird's beak and causing a lateral mote encroachment of 0.2 micrometers into each active region, thereby wasting precious silicon real estate. There have been various modified LOCOS and other isolation schemes proposed to minimize this lateral encroachment. A notable example is shallow trench isolation, STI, which involves using reactive ion etching to etch a shallow, 1 ohm, trench or groove in the silicon substrate after the isolation pattern, filling it up completely by deposition of a dielectric layer of silicon dioxide and polysilicon by LPCVD, and then using chemical mechanical polishing, CMP, to planarize the structure, Fig 9.6. This consumes less silicon real estate compared with LOCOS, but gives superior isolation because the sharp corners at the bottom of the trench give rise to potential barriers that block leakage currents, the corner effect. The pad oxide between the nitride and the Si surface minimizes the stress due to the nitride, and prevents bonding of the nitride to the silicon, as mentioned above. Any residual nitride on the silicon would retard subsequent gate oxide formation, leading to weak spots in the gate region of the MOSFETs. This problem is known as the white ribbon effect or the Cooey effect, after the Dutch scientist who first identified it. The pad oxide mitigates this problem, but does not solve it completely. Therefore, very often a sacrificial or dummy oxide is grown to consume a layer of silicon containing any residual nitride, and this oxide is wet etched prior to the growth of the actual gate oxide. In many modern CMOS processes, LOCOS has been supplanted by STI. Here, we use RE to etch shallow grooves or trenches, 0.2 micrometers deep, in the isolation regions. After growing a thin thermal oxide to passivate the surface, we fill up the trench with LPCVD oxide and grind the surface flat with CMP. STI has no mote encroachment, unlike LOCOS, and is capable of superior electrical isolation using less silicon real estate. Next, an ultra-thin, 0.3 nanometers, gate oxide is grown on the substrate. Since the electrical quality of this oxide and its interface with the silicon substrate is of paramount importance to the operation of the MOSFETs, dry oxidation is used for this step. This is followed by deposition of a high-K gate dielectric. It is immediately covered with LPCVD polysilicon or a metal gate electrode in order to minimize contamination of the gate oxide. The polysilicon gate layer is doped very heavily, typically N+ using a phosphorus dopant source, phosphor oxide chloride in a diffusion furnace, all the way to the polysilicon oxide interface in order to make it behave electrically like a metal electrode. Alternatively, the LPCVD polysilicon film may also be in situ doped during the deposition itself by flowing in an appropriate dopant gas such as phosphine or diborane. Heavy doping of the gate material is very important, because otherwise a depletion layer can be formed in the polysilicon gate, the poly-depletion effect. This could result in a depletion capacitance in series with the gate oxide capacitance, thereby reducing the overall gate capacitance and, therefore, the drive current CEQ. 653. The high doping, 100,000 quadrillions per cubic centimeter, in the polysilicon gate is also important for reducing the resistance of the gate and its RC time constant. The uniformly high doping in the polysilicon layer is facilitated by the presence of the grain boundary defects in the film, because diffusivity of dopants along grain boundaries is many orders of magnitude higher than in single crystal silicon. If metal gate electrodes such as titanium nitride are used, these problems go away. Sometimes, a polysilicon gate may be deposited on a thin metal gate electrode to make a composite structure. The doped polysilicon layer or metal gate is then patterned to form the gates, and etched anisotropically by reactive ion etching to achieve vertical side walls. That is extremely important because this etched gate is used as a self-aligned implant mask for the source drain implants. As mentioned above, self-aligned processes are always desirable in terms of process simplicity and packing density. It is particularly useful in this case because we thereby guarantee that there will be some overlap of the gate with the source drain but minimal overlap. The overlap is determined by the lateral scattering of the ions and by the lateral diffusion of the dopants during subsequent thermal processing, such as source/drain implant anneals. If there were no overlap, the channel would have to be turned on in this region by the gate fringing fields. The resulting potential barrier in the channel would degrade the device current. On the other hand, if there is too much overlap, it leads to an overlap capacitance between the source or drain and the gate. This is particularly bothersome near the drain end because it leads to the Miller overlap capacitance, which causes undesired capacitive feedback between the output drain terminal and the input gate terminal, see section 6.5.8. Fabrication steps for the N-channel MOSFETs in the P-well are shown in Fig 9.7. After the polysilicon gate is etched, we first do a self-aligned N-type source drain implant, during which the tank masking level is used to protect the PMOS devices with a layer of photoresist. The NMOS source and drain implants are done in two stages. The first implant is a lightly doped drain, LDD, implant, Fig 9.7a. This is typically a dose of 10 trillion to 100 trillion of atoms per cubic centimeter, corresponding to a concentration of 1,000 quadrillions to 10,000 quadrillions of atoms per cubic centimeter, and an ultra-shallow junction depth of 50 to 100 nanometers. When a MOSFET is operated in the saturation region, the drain channel junction is reverse biased, resulting in a very high electric field in the pinch-off region. As we saw in section 5.4 for Revere-Ebiest PN junctions, reducing the doping level increases the depletion width and makes the peak electric field at the junction smaller. As discussed in section 6.5.9, electrons traveling from the source to the drain in the channel can gain kinetic energy and thereby become hot electrons, which create damage. The low doping in the lightly doped drain helps reduce hot carrier effects at the drain end. The shallow junction depths in the lightly doped drain are also important for reducing short channel effects such as DIBL and charge sharing, sections 6.5.10 and 6.5.11. The penalty that we pay with the use of an lightly doped drain region is that the source-to-drain series resistance goes up, which degrades the drive current. As the technology is evolving toward lower power supply voltages, hot carrier effects are becoming less important. This, along with the need to reduce series resistance, has driven the trend toward increasing doping in the lightly doped drain to levels above 10,000 quadrillion of atoms per cubic centimeter. In fact, the use of the term lightly doped drain then becomes a bit of a misnomer, and is often replaced by the term source/drain extension or tip. After the lightly doped drain regions are formed alongside the polysilicon gate, we implant deeper, 200 nanometers, and more heavily doped, 100,000 quadrillion per cubic centimeter, source and drain junctions farther away from the gate edges, Fig 9.7d. This more conductive region allows ohmic contacts to the source and drain to be formed more easily than they could be directly to the lightly doped drain regions, and reduces the source-drain series resistance. This implant is done using a self-aligned scheme by the formation of sidewall oxide spacers. After removing the photoresist covering the PMOS devices, we deposit conformal LPCVD oxide, 100 to 200 nanometers thick, using an organic precursor called tetraethyl orthosilicate, TEOS, over the entire wafer at fairly high temperatures, 700 degrees Celsius, Fig 9.7b. The term conformal means that the deposited film has the same thickness everywhere, and follows the topography on the wafer. This oxide layer is then subjected to Re, which is anisotropic, i.e., it etches predominantly in the vertical direction, section 5.1.7. If the reactive ion etching step is timed to just etch off the deposited oxide on the flat surfaces, it leaves oxide sidewall spacers on the edges of the polysilicon gate, as shown in Fig 9.7c. This sidewall spacer is used as a self-aligned mask to protect the lightly doped drain regions very near the gate during the heavier, deeper N+ source and drain implants, Fig 9.7d. Figure 9.7 Fabrication of the lightly doped drain structure, using sidewall spacers. The polysilicon gate covers the thin gate oxide and masks the first low-dose implant, A. A thick layer is deposited by CVD, B, and is anisotropically etched away to leave only the sidewall spacers, C. These spacers serve as a mask for the second, high-dose implant. After a drive-in diffusion, the lightly doped drain structure results, D. Next, the NMOS devices are masked by photoresist, and a P+ source and drain implant is done for the PMOS FETs, Fig 9.8a. It may be noted that an lightly doped drain was not used for the PMOS. This is due to the fact that hot hole effects are less problematic than hot electron degradation, partly due to the lower hole mobility and partly due to the higher silicon-silicon dioxide barrier in the valence band, 5 electron volts, than in the conduction band, 3.1 electrovolts. After the source drain implants are done, the dopants are activated and the ion implant damage is healed by a furnace anneal, or more frequently using a rapid thermal anneal. In this anneal we use the minimum acceptable temperature and time combination, the thermal budget, because it is critically important to keep the dopant profiles as compact as possible in ultra-small MOS FETs. We can now appreciate why most CMOS logic devices are made on P-type substrates, rather than N-type. The N-channel MOS FETs generate a lot more substrate current due to hot carrier effects than PMOS FETs. The holes, thus generated, can more easily flow to ground in a P-type substrate, than in an N substrate. Also, it is easier to dope substrates P-type with B during Czochralski crystal growth than N-type with antimony. Antimony is the preferred donor, rather than arsine or phosphor for bulk doping of the silicon melt, because antimony evaporates less than the other species. The use of N+ polysilicon gates for both NMOS and PMOS devices raises some interesting device issues. Since the Fermi level in the N+ gate is very close to the silicon conduction band, its work function is well suited to achieving a low threshold voltage for NMOS, FMS-1V, but not for PMOS, FMS 0 volts. From the threshold voltage expression EQ 638, we notice that the second and third terms approach zero as thin oxide technology evolves because CI is getting larger. For high drive current we want threshold voltage to be in the neighborhood of 0.3 to 0.7 volts for NMOS, minus 0.3 to minus 0.7 volts for PMOS. We find from EQ 638, that the P-well doping can be optimized to achieve the correct threshold voltage for the NMOS transistor, while at the same time being high enough to prevent punch-through breakdown between source and drain. For the PMOS transistor, on the other hand, an N-well doping of the order of 1000 quadrillions per cubic centimeter prevents punch-through, but the Fermi potential, HF, is so large and negative that the threshold voltage is too negative. That forces us to do a separate acceptor implant to adjust threshold voltage for the PMOS devices, Fig 9.8b. The acceptor dose is low enough that the P layer is fully depleted at zero gate bias, leading to enhancement mode, rather than depletion mode, transistors. In CMOS we try to make the negative threshold voltage of the PMOS device about the same value as the positive threshold voltage of the NMOS. Close examination of the band diagram in the channel of the PMOS FET along the vertical direction, perpendicular to the gate oxide, shows that the energy minimum for the holes in the inversion layer is slightly below 100 nanometers, the oxide-silicon interface, leading to what is known as buried channel operation for PMOS, Fig 9.8c. On the other hand, for NMOS, the electron energy minimum in the inversion layer occurs right at the oxide-silicon interface, leading to surface channel operation. Figure 9.8 Buried channel PMOS, A, self-aligned P plus source drain implant with no LDD using photoresist to protect NMOS FETs. A P-type threshold voltage adjust implant is shown in color in the channel. B, doping profile as a function of depth in the middle of the channel, showing the P-type threshold voltage adjust implant near the surface. C, electron potential energy as a function of depth in the middle of the channel, showing holes collecting in the buried channel. For higher gate bias, the PMOS operation changes to a surface channel, as indicated by the dashed line. There are good and bad aspects of this buried channel behavior for PMOS. Since the holes in the inversion layer of the PMOS FET travel slightly away from the oxide-silicon interface, they do not suffer as much channel mobility degradation as the electrons in the NMOS FET due to surface roughness scattering. That is good, because hole mobilities in silicon are generally lower than electron mobilities, which forces us to make PMOS devices wider than the NMOS FETs to get similar drive currents. However, buried channel devices have a greater propensity toward DIBL and punch-through breakdown. Hence, as the size of MOS FETs is reduced, the DIBL problem becomes worse, and there is a desire to have surface channel operation for both NMOS and PMOS. Thus, there is interest in so-called dual-gate CMOS, where N+ polysilicon gates are used for NMOS FETs and P+ gates are used for PMOS FETs. Such dual work function gates can be achieved by depositing the polysilicon undoped and then using the source and drain implants themselves to also dope the gates appropriately. This approach exploits the high polysilicon grain boundary diffusivities to degenerately dope the gates, at the same time having ultra-shallow source and drain junctions to minimize DIBL. As a historical footnote, it may be added that MOS FETs initially used aluminum gates which could not withstand high-temperature processing. Hence, the source and drain regions had to be formed first, either by diffusion or by implant, and then the aluminum gate was deposited and patterned. Such non-self-aligned processes suffered from the Miller capacitance mentioned previously. What made self-aligned source and drain regions viable was the use of polysilicon, which has a sufficiently high melting point to withstand subsequent processing. Recent research on MOSFET technology is going back full circle to metal gates, but this time using refractory metals such as tungsten, W. These metals have better conductivity than heavily doped polysilicon, and a work function that is better suited for CMOS. The Fermi level of W is near the middle of the silicon band gap, which makes the flat band voltage and the threshold voltage more symmetric and better matched between NMOS and PMOS, and avoids the buried channel effect. The next step is to form a metal silicon alloy or silicide in the source/drain and gate regions of the MOS FETs in order to reduce the series resistance, and thereby the RC time constants, and increase the drive current. This involves depositing a thin layer of a refractory metal such as titanium over the entire wafer by sputtering, and reacting the titanium with silicon wherever they come in direct contact, by doing a two-step heat treatment in an N-ambient, Fig 9.9a. A 600 degrees Celsius anneal results in the formation of titanium silicide, the C49 phase according to metallurgists, which has fairly high resistivity, followed by an 800 degrees Celsius anneal which converts the titanium silicide to the C54 phase, titanium silicide, which has an extremely low resistivity of 17 microohms per centimeter, much lower than that of the most heavily doped silicon. Figure 9.9 The formation of silicide source drain and gate regions for low resistance contacts. A layer of refractory metal is deposited and reacted in regions of exposed silicon to form a conducting silicide layer. B. The unreacted metal is removed and a CVD glass is deposited and patterned for contact metallization. C. Cross-sectional micrograph of lightly doped drain metal oxide semiconductor field effect transistor with gate length of 52 nanometers. Photograph courtesy of Texas Instruments. On the other hand, the titanium on top of the sidewall oxide spacers does not form a silicide and stays as unreacted titanium or forms tin because the process is done in a nitrogen ambient. The titanium and titanium nitride can be etched off selectively by using a wet hydrogen peroxide-based etch, which does not attack the titanium disilicide, thereby electrically isolating the gates from the source/drains. Note that this process results in a salicide without a separate masking level only on the source/drains and the polysilicon gate, where the silicide is often termed a polyside. This results in very high-performance MOSFETs. Finally, the MOSFETs have to be properly interconnected according to the circuit layout, using the metallization level. This involves LPCVD of an oxide dielectric layer doped with boron and phosphor, which is known as borophosphosilicate glass, BPSG, on the entire wafer, patterning it by means of the contact level reticle and using reactive ion etching to open up the contact holes to the substrate, Fig 9.9b. The boron and phosphor allow the oxide layer to soften and reflow more readily upon annealing, thereby helping planarize or smooth out the topography on the wafer. This shaping of the millions of very small contact holes is critical on a ULSI chip, because otherwise metal deposited on the surface into the contact holes may not reach completely into the holes, leading to a catastrophic open circuit. In fact, sometimes a CVD tungsten layer is selectively deposited in the contact holes to form a contact plug before one proceeds to the next step. Then a suitable metal layer such as aluminum, alloyed with 1% silicon and 4% copper, is sputter deposited over the wafer, patterned using the metal interconnect level, and subjected to metal reactive ion etching. The silicon is added to the aluminum to solve the junction spiking problem, whereby pure aluminum can incorporate the solid solubility limit of Si from the shallow source/drain regions. This would allow the aluminum to spike, or short, through the PN junction. The copper is added to enlarge the grain size in the aluminum interconnect films, which are polycrystalline, making it harder for the electrons moving during current flow to nudge the aluminum atoms along, thereby opening voids, producing open circuits, in the interconnect. This is an example of an electromigration phenomenon. A cross-sectional picture of an lightly doped drain MOSFET with salicide is shown in Fig 9.9c. In a modern ULSI chip, the complexity of the device layout generally demands that multiple levels of metallization be used for interconnecting the devices, Fig 9.10. Hence, after the first metal is deposited, an intermetal dielectric isolation layer such as silicon dioxide is deposited by low-temperature CVD. Low temperatures are very important in this back-end part of the processing because by now all the active devices are in place and one cannot allow the dopants to diffuse significantly. Also, the metallization cannot withstand temperatures higher than 500 Celsius degrees. The dielectric isolation layer must be suitably planarized prior to the deposition of the next layer of metal, and this is generally done by CMP. Planarization is important because if metal is deposited on a surface with rough topography and subjected to reactive ion etching, there can be residual metal sidewall filaments or stringers at the steps. For the same reason one gets sidewall oxide spacers on either side of the metal oxide semiconductor field effect transistor gate in Fig 9.7. These metal stringers can cause short circuits between adjacent metal lines. Planarization is also important in maintaining good depth of focus during photolithography. Figure 9.10 Multilevel interconnect, cross-section of integrated circuit showing levels of copper interconnections with suitably planarized intermetal dielectrics. The transistors are at the very bottom and correspond to 22 nanometers complementary metal oxide semiconductor. Photograph courtesy of Intel. After planarization of the isolation layer, one uses photolithography to open up a new set of contact holes called vias, followed by deposition, patterning and reactive ion etching of the next layer of metal, and so on for multi-level metallization. As mentioned previously, Wolfram tungsten metal plugs are sometimes selectively deposited to fill up the via holes prior to the metal deposition, and reduce the likelihood of an open circuit. Finally, a protective overcoat is deposited on the integrated circuit to prevent contamination and failure of the devices due to the ambient, Fig 910. This generally involves plasma CVD of silicon nitride, which has the nice attribute that it blocks the diffusion of water vapor and sodium through it. Sodium, as mentioned in section 6.4.3, causes a mobile ion problem in the gate dielectric of metal oxide semiconductor devices. Sometimes, the protective overcoat is a BPSG layer. After the overcoat is deposited, openings are etched for the metal bond pads. After the chips are tested in an automated tester, the known good dies are packaged and wire bonded, as discussed in section 9.6. Integration of other circuit elements. One of the most revolutionary developments of integrated circuit technology is the fact that integrated transistors are cheaper to make than are more mundane elements such as resistors and capacitors. There are, however, numerous applications calling for diodes, resistors, capacitors, and inductors in integrated form. In this section we discuss briefly how these circuit elements can be implemented on the chip. We will also discuss a very important circuit element, the interconnection pattern that ties all of the integrated devices together in a working system. Diodes. It is simple to build p-n junction diodes in a monolithic circuit. It is also common practice to use transistors to perform diode functions. Since many transistors are included in a monolithic circuit, no special diffusion step is required to fabricate the diode element. There are a number of ways in which a transistor can be connected as a diode. Perhaps the most common method is to use the emitter junction as the diode, with the collector and base shorted. This configuration is essentially the narrow base diode structure, which has high switching speed with little charge storage, Prop 5.40. Since all the transistors can be made simultaneously, the proper connections can be included in the metallization pattern to convert some of the transistors into diodes. Resistors. Diffused or implanted resistors can be obtained in monolithic circuits by using the shallow junctions used in forming the transistor regions, Fig 911a. For example, during the base implant, a resistor can be implanted which is made up of a thin p-type layer within one of the n-type islands. Alternatively, a p region can be made during the base implant, and an n-type resistor channel can be included within the resulting p region during the emitter implant step. In either case, the resistance channel can be isolated from the rest of the circuit by proper biasing of the surrounding material. For example, if the resistor is a p-type channel obtained during the base implant, the surrounding N material can be connected to the most positive potential in the circuit to provide reverse bias junction isolation. The resistance of the channel depends on its length, width, depth of the implant, and resistivity of the implanted material. Since the depth and resistivity are determined by the requirements of the base or emitter implant, the variable parameters are the length and width. Two typical resistor geometries are shown in Fig 911b. In each case the resistor is long compared with its width, and a provision is made on each end for making contact to the metallization pattern. Design of diffused resistors begins with a quantity called the sheet resistance of the diffused layer. If the average resistivity of a diffused region is T, the resistance of a given length L is resistance equal ohms per meter multiplied by length divided by cross-section area of the wire, where W is the width and T is the thickness of the layer. Now if we consider one square of the material, such that L equal W, we have the sheet resistance Rs T/T in units of ohms per square. We notice that R measured for a given layer is numerically the same for any size square. This quantity is simple to measure for a thin diffused layer by a 4-point probe technique. Therefore, for a given diffusion, the sheet resistance is generally known with good accuracy. The resistance then can be calculated from the known value of resistance and the ratio length/width, the aspect ratio, for the resistor. Figure 9:11 Monolithic resistors. A. Cross-section showing use of base and emitter diffusions for resistors. B. Top view of two resistor patterns. We can make the width W as small as possible within the requirements of heat dissipation and photolithographic limitations and then calculate the required length from W and Rs. Design criteria for diffused resistors include geometrical factors, such as the presence of high current density at the inside corner of a sharp turn. In some cases it is necessary to round corners slightly in a folded or zigzag resistor, Fig 912b, to reduce this problem. To reduce the amount of space used for resistors or to obtain larger resistance values, it is often necessary to obtain surface layers having larger sheet resistance than is available during the standard base or emitter implants. We can use a different implant, such as the threshold voltage adjust implant, to form shallow regions having very high sheet resistance, 100 kOhms per square. This procedure can provide a considerable saving of space on the chip. In integrated FET circuits it is common to replace load resistors with depletion mode transistors, as mentioned in section 6.5.5. Capacitors. One of the most important elements of an integrated circuit is the capacitor. This is particularly true in the case of memory circuits, where charge is stored in a capacitor for each bit of information. Figure 912 illustrates a 1-transistor DRAM cell, in which the N-channel MOS transistor provides access to the adjacent MOS capacitor. The top plate of the capacitor is polysilicon, and the bottom plate is an inversion charge contacted by an N+ region of the transistor. The terms bit line and word line refer to the row and column organization of the memory, section 9.5.2. One can also make use of the capacitance associated with p-n junctions, as discussed in section 5.5.5. Figure 912 Integrated capacitor for dynamic random access memory cells. A 1-transistor memory cell in which the transistor stores and accesses charge in an adjacent planar metal oxide semiconductor capacitor. Inductors. Inductors have not been incorporated into integrated circuits in the past, because it is much harder to integrate inductors than the other circuit elements. Also, there has not been a great need for integrating inductors. Recently, that has changed because of the growing need for radio frequency analog integrated circuits for portable communication electronics. Inductors are very important for such applications, and can be made with reasonable Q factors using spiral wound thin metal films on an integrated circuits. Such spiral patterns can be defined by photolithography and etching techniques compatible with integrated circuit processing, or they can be incorporated in a hybrid integrated circuits. Contacts and interconnections. During the metallization step, the various regions of each circuit element are contacted and proper interconnection of the circuit elements is made. Aluminum is commonly used for the top metallization, since it adheres well to silicon and to silicon dioxide if the temperature is raised briefly to about 550 degrees Celsius after deposition. Gold is used on gallium arsenide devices, but the adhesion properties of gold to silicon and silicon dioxide are poor. Gold also creates deep traps in silicon. As mentioned throughout this chapter, silicide contacts and doped polysilicon conductors are commonly used in integrated circuits. By opening windows through the oxide layers to these conductors, aluminum metallization can be used to contact them and connect them to other parts of the circuit. In cases where aluminum is used to contact the silicon surface, it is usually necessary to use aluminum containing about 1% silicon to prevent the metal from incorporating silicon from the layer being contacted, thereby causing spikes in the surface. Thin diffusion barriers are also used between the aluminum and silicon layers, to prevent migration between the two. The refractory silicides mentioned in section 9.3.1 serve this purpose. Increased complexity and packing density in integrated circuits inevitably leads to a need for multi-layer metallization. Multiple levels of copper metallization can be incorporated with interspersing dielectrics. In general, the metals may all be aluminum, copper, or they may be different conductors such as polysilicon or refractory metals, depending on the heat each is subjected to in subsequent processing. Also, the dielectrics may be deposited oxides, borophosphosilicate glass for reflow planarization, nitrides, and so on. The planarization of the surface is extremely important to prevent breaks in the metallization, which can occur in traversing a step on the surface. Various approaches using reflow glass, polyamide, and other materials to achieve planarization have been used, along with CMP. The most important challenge in designing interconnects is the RC time constant, which affects the speed and active power dissipation of the chip. A very simplistic model of two layers of interconnects with an intermetal dielectric, Figs 913 and 914, shows that it can be regarded as a parallel plate capacitor. Regarding the interconnect as a rectangular resistor, its resistance is given by where Rs is the sheet resistance, and the other symbols are defined in Fig 914. The capacitance is given by the resistance times capacitance time constant is then. Interestingly, for this simple one-dimensional model, the width of the interconnect W cancels out. Therefore, it does not make sense to use wider conductors for high-speed operation. It is also impractical to do so in terms of packing density. Of course, in reality we must account for the fringing electric fields, and therefore account for width dependence. From EQ 9.2, it is clear we need as thick a metal layer, within practical limits of deposition times and etching times, and as low a resistivity as possible. Figure 913 Multilevel interconnects, micrograph of multilevel interconnects in an integrated circuit. The interlevel dielectrics have been etched off to reveal the copper interconnect lines. Photograph courtesy of IBM. Low resistivities are also important in minimizing ohmic voltage drops in metal bus lines that carry power from one end of a chip to the other. Aluminum is very good in this regard, and thus was a mainstay for silicon technology for many years. Aluminum also has other nice attributes such as good ohmic contacts to both N and P-type silicon, and good adhesion to oxides. Figure 914 Equivalent circuit illustrating the various parasitic capacitive elements associated with a multilevel interconnect. On the top right-hand corner of the figure, we focus on the parallel plate capacitor model referred to in EQs 9.1 and 9.2. Copper has even lower resistivity, 1.7 microohms per centimeter, than aluminum, 3 microohms per centimeter, and is about 2 orders of magnitude less susceptible to electromigration. Hence, it is an excellent alternative to aluminum for very high-speed integrated circuits, Fig 913. The process breakthroughs that have made copper viable for metallization include new electrodeposition and electroplating techniques because CVD or sputter deposition is not very practical for copper. It is also very difficult to use reactive ion etching for copper because the etch byproducts for copper are not very volatile. Hence, instead of reactive ion etching, copper patterning is based on the so-called Damascene process where grooves are first etched in a dielectric layer, copper is deposited on it, and the metal layer is mechanically polished down, leaving inlaid metal lines in the oxide grooves. In this method, the metal does not have to be etched directly using reactive ion etching, which is always a difficult process. The name Damascene is derived from a metallurgical technique in ancient Turkey where metal artwork was inlaid into swords and other artifacts using this type of process. Copper can create traps deep in the band gap of silicon, hence, a suitable barrier layer such as titanium is needed between the copper layer and the silicon substrate. Other parameters in EQ 9.2 that can minimize the RC time constant are clearly the use of a thick intermetal dielectric layer, once again within the limits of practicality in terms of deposition times, and as low a dielectric constant material as possible. Silicon dioxide has a relative dielectric constant of 3.9. There is active research in low dielectric constant materials, sometimes referred to as low-K materials. These include organic materials such as polyamides, or aerogels which have air pockets or porosity purposely built in to minimize the dielectric constant. In designing the layout of elements for a monolithic circuit, topological problems must be solved to provide efficient interconnection without crossovers, points at which one conductor crosses another conductor. If crossovers must be made on the silicon surface, they can be accomplished easily at a resistor. Since the implanted or diffused resistor is covered by silicon dioxide, a conductor can be deposited crossing the insulated resistor. In cases requiring crossovers where no resistor is available, a low-value implanted resistor can be inserted in one of the conductor paths. For example, a short N+ region can be implanted during the source/drain step and contacted at each end by one of the conductors. The other conductor can then cross over the oxide layer above the N+ region. Usually, this can be accomplished without appreciable increase in resistance, since the N+ region is heavily doped and its length can be made small. During the metallization step, appropriate points in the circuit are connected to relatively large pads to provide for external contacts. These metal pads are visible in photographs of monolithic circuits as rectangular areas spaced around the periphery of the device. In the mounting and packaging process, these pads are contacted by small gold or aluminum wires or by special techniques such as those discussed in section 9.6. One of the most interesting and broadly useful integrated devices is the charge-coupled device, CCD. The CCD is part of a broader class of structures known generally as charge transfer devices. These are dynamic devices that move charge along a predetermined path under the control of clock pulses. These devices find applications in signal processing and imaging. In this section we lay the groundwork for understanding these devices, but their present forms and variety of applications must be found in the current literature. Dynamic effects in metal oxide semiconductor capacitors. The basis of the CCD is the dynamic storage and withdrawal of charge in a series of metal oxide semiconductor capacitors. Thus we must begin by extending the MOS discussion of Chapter 6 to include the basics of dynamic effects. Figure 9.15 shows an MOS capacitor on a p-type substrate with a large positive gate pulse applied. A depletion region exists under the gate, and the surface potential increases considerably under the gate electrode. In effect, the surface potential forms a potential well, which can be exploited for the storage of charge. If the positive gate bias has been applied for a sufficiently long time, electrons accumulate at the surface and the steady-state inversion condition is established. The source of these carriers is the thermal generation of electrons at or near the surface. In effect, the inversion charge tells us the capacity of the well for storage charge. The time required to fill the well thermally is called the thermal relaxation time, and it depends on the quality of the semiconductor material and its interface with the insulator. For good materials, the thermal relaxation time can be much longer than the charge storage times involved in CCD operation. If instead of a steady-state bias we apply a large positive pulse to the metal oxide semiconductor gate electrode, a deep potential well is first created. Before inversion has occurred by thermal generation, the depletion width is greater than it would be at equilibrium, W greater than Wm. This transient condition is sometimes called deep depletion. If we can inject electrons into this potential well electrically or optically, they will be stored there. The storage is temporary, however, because we must move the electrons out to another storage location before thermal generation becomes appreciable. Figure 9.15 An MOS capacitor with a positive gate pulse, A, depletion region and surface charge, B, potential well at the interface, partially filled with electrons corresponding to the surface charge shown in A. What is needed is a simple method for allowing charge to flow from one potential well to an adjacent one quickly and without losing much charge in the process. If this is accomplished, we can inject, move, and collect packets of charge dynamically to do a variety of electronic functions. The basic charge-coupled device. The original charge-coupled device structure proposed in 1969 by Boyle and Smith of Bell Laboratories consisted of a series of metal electrodes forming an array of metal oxide semiconductor capacitors as shown in Fig 9.16. Voltage pulses are supplied in 3 lines, L1, L2, L3, each connected to every third electrode in the row, G1, G2, G3. These voltages are clocked to provide potential wells, which vary with time as in Fig 9.16. At time t1 a potential well exists under each G1 electrode, and we assume this well contains a packet of electrons from a previous operation. At time t2 a potential is applied also to the adjacent electrode G2, and the charge equalizes across the common G1, G2 well. It is easy to visualize this process by thinking of the mobile charge in analogy with a fluid, which flows to equalize its level in the expanding container. Figure 9.16 the basic charge-coupled device, composed of a linear array of metal oxide semiconductor capacitors. At time t1, the G1 electrodes are positive, and the charge packet is stored in the G1 potential well. At T2 both G1 and G2 are positive, and the charge is distributed between the two wells. At T3 the potential on G1 is reduced, and the charge flows to the second well. At T4 the transfer of charge to the G2 well is completed. This fluid model continues at T3 when V1 is reduced, thus decreasing the potential well under G1. Now the charge flows into the G2 well, and this process is completed at T4 when V1 is 0. By this process the packet of charge has been moved from under G1 to G2. As the procedure is continued, the charge is next passed to the G3 position, and continues down the line as time proceeds. In this way charge can be injected using an input diode, transported down the line, and detected at the other end. Improvements on the basic structure. Several problems arise in the implementation of the charge-coupled device structure of Fig 9.16. For example, the separation between electrodes must be very small to allow coupling between the wells. An improvement can be made by using an overlapping gate structure such as that shown in Fig 9.17. This can be done, for example, with polysilicon electrodes separated by silicon dioxide or with alternating polysilicon and metal electrodes. One of the problems inherent to the charge transfer process is that some charge is inevitably lost during the many transfers along the charge-coupled device. If the charges are stored at the silicon-silicon dioxide interface, surface states trap a certain amount of charge. Thus if the zero logic condition is an empty well, the leading edge of a train of pulses is degraded by the loss of charge required in filling the traps which were empty in the zero condition. One way of improving this situation is to provide enough bias in the zero state to accommodate the interface and bulk traps. This procedure is colorfully referred to as using a fat zero. Even with the use of fat zeros, the signal is degraded after a number of transfers, by inherent inefficiencies in the transfer process. Transfer efficiency can be improved by moving the charge transfer layer below the semiconductor insulator interface. This can be accomplished by using ion implantation or epitaxial growth to create a layer of opposite type than the substrate. This shifts the maximum potential under each electrode into the semiconductor bulk, thus avoiding the semiconductor insulator interface. This type of device is referred to as a buried channel charge-coupled device. The three-phase charge-coupled device shown in Fig 9.16 is only one example of a variety of charge-coupled device structures. Figure 9.18 illustrates one method for achieving a two-phase system, in which voltages are sequentially applied to alternating gate electrodes from two lines. Figure 9.17 an overlapping gate charge-coupled device structure. One set of electrodes is polycrystalline silicon, and the overlapping gates are aluminum in this case. Silicon dioxide separates the adjacent electrodes. Figure 9.18 a two-phase charge-coupled device with an extra potential well built in under the right half of each electrode by donor implantation. A two-level polysilicon gate structure is used, in which the gate electrodes overlap, and a donor implant near the silicon surface creates a built-in well under half of each electrode. When both gates are turned off, potential wells exist only under the implanted regions, and charge can be stored in any of these wells. With electrode G2 pulsed positively, the charge packet shown in B is transferred to the deepest well under G2, which is its implanted region as C, indicates. Then with both gates off, the wells appear as in B, again, except that the charge is now under the G2 electrode. The next step in the transfer process is obviously to pulse G1 positively, so that the charge moves to the implanted region under the G1 electrode to the right. Other improvements to the basic structure are important in various applications. These include channel stops or other methods for achieving lateral confinement for the stored charge. Regeneration points must be included in the array to refresh the signal after it has been degraded. Applications of charge-coupled devices. Charge-coupled devices are used in a number of ways, including signal processing functions such as delay, filtering, and multiplexing several signals. Another interesting application of charge-coupled devices is in imaging for astronomy or in solid-state cameras, in which an array of photosensors is used to form charge packets proportional to light intensity, and these packets are shifted to a detector point for readout. There are numerous ways of accomplishing this in charge-coupled devices, including the linear array line scanner, in which the second dimension is obtained by moving the scanner relative to the image. Alternatively, an area image sensor can be made which scans the image electronically in both dimensions. The latter device can be used as an alternative to the electron beam addressed television imaging tube, Fig 919. Figure 919. A charge-coupled device image sensor shown as large white rectangular areas, with peripheral signal processing circuitry. Photograph courtesy of Texas Instruments. In the early development of integrated circuits, it was felt that the inevitable defects that occur in processing would prevent the fabrication of devices containing more than a few dozen logic gates. One approach to integration on a larger scale tried in the late 1960s involved fabricating many identical logic gates on a wafer, testing them, and interconnecting the good ones, a process called discretionary wiring. While this approach was being developed, however, radical improvements were made in device processing which increased the yield of good chips on a wafer dramatically. By the early 1970s it was possible to build circuits with many hundreds of components per chip, with reasonable yield. These improvements made discretionary wiring obsolete almost as soon as it was developed. By reducing the number of processing defects, improving the packing density of components, and increasing the wafer size, it is now possible to place millions of device elements on a single chip of silicon and to obtain many perfect chips per wafer. A major factor in the development of integrated circuits has been the continual reduction in size of the individual elements, transistors, capacitors, within each circuit. Through improved design and better lithography, there has been a dramatic shrinking of the minimum feature size, for example, a transistor gate, used in these devices. The results of shrinking the elements in a 256 MB dynamic random access memory are shown in Fig 920. By reducing the minimum feature size in successive steps from 0.13 to 0.11 micrometers, the die area was reduced from about 135 square millimeters in the first generation design to less than 42 square millimeters in the fifth generation device. Figure 920. Size reduction of a 256 MB dynamic random access memory die as the minimum feature size is reduced from 0.13 micrometers for the first generation design, die on the left, to 0.11 micrometers for the die on the right. 2004 Micron Technology, Incorporated. Obviously, more of the smaller chips can be made by batch fabrication on the wafer, and the effort in shrinking the design is rewarded in a more profitable device. Successive designs using reduced feature sizes have made dramatically increased circuit complexity possible. Dynamic random access memory design has set the pace over the past 2 decades, in which successive 1 MB, 4 MB, and 16 MB memories led to similar powers of 2 increase to the gigabytes range. Figure 921 illustrates the size comparison of a 128 MB memory with an equivalent amount of memory in the form of 2 64 MB and 8 16 MB chips. These are examples of ULSI. Although the achievement of many powers of 2 in memory is impressive and important, other ULSI chips are important for the integration of many different system functions. A microprocessor includes functions for a computer central processing unit, CPU, along with memory, control, timing, and interface circuits required to perform very complex computing functions. Figure 9.21 3 ways of obtaining 128 million bits of dynamic random access memory, A. 128 megabyte chip, B. 264 megabyte chips, C. 816 megabyte chips. The 128 megabyte die measures almost 1 by 1 inch. 2004 Micron Technology, Incorporated. The complexity of such devices is shown in Fig 922, which illustrates a microprocessor chip. Before leaving this section, it might be useful to provide some calibration regarding the dimensions we have been discussing. Figure 923 compares the size of 64 megabyte dynamic random access memory circuit interconnect elements with a human hair, on the same scale. We can see that the densely packed 0.18 micrometer lines on this ULSI memory chip are dwarfed by the scanning electron micrograph of a human hair, which has the diameter of about 50 microns. Current generation dynamic random access memories have feature sizes of 25 nanometers, 0.025 micrometers. Although the focus of this book is devices and not circuits, it is important to look at some typical applications of metal oxide semiconductor capacitors and field effect transistors in semiconductor logic and memory ULSI, which constitute about 90% of all integrated circuits. This should give the reader a better feel for why we have studied the physics of metal oxide semiconductor devices in Chapter 6. This is clearly not a comprehensive discussion, because the design and analysis of circuits is a large subject covered in other books and courses. We will first look at some digital logic applications, followed by some typical memory devices. Logic devices. A very simple and basic circuit element is the inverter, which serves to flip the logic state. When its input voltage is high, corresponding to logic 1, its output voltage is low, logic 0, and vice versa. Let us start the analysis with a resistor-loaded N-channel MOSFET inverter to illustrate the principles in the simplest possible manner, Fig 924a. Figure 922 an example of ULSI, the Intel 22 nanometers quad-core processor with 1.4 billion transistors. Photograph courtesy of Intel. Figure 923 size comparison of ULSI circuit elements with human hair, A. Densely packed 0.18 micrometers interconnect lines in the array of a 64 megabyte dynamic random access memory chip, B. Scanning electron micrograph of a human hair. Both micrographs are shown to the same scale. 2004 Micron Technology, Incorporated. Then, we will extend the treatment to the slightly more complicated CMOS inverters, which are much more useful and more common today. A key concept for inverters is the voltage transfer characteristic, VTC, which is a plot of the output voltage as a function of the input bias, Fig 924c. The VTC gives us information, for example, about how much noise the digital circuit can handle, and the speed of switching of the logic gates. There are 5 key operating points, marked I through V, on the VTC. They include VOH, corresponding to the logic high or 1, vol, corresponding to the logic low or 0, and Vm, corresponding to the intersection of a line with unity slope, where Vout equal Ven, with the VTC. Vm, known as the logic threshold, not to be confused with the threshold voltage of the metal oxide semiconductor field effect transistors, is important when two inverters are cross-coupled in a flip-flop circuit because the output of one is fed to the input of the other, and vice versa. Figure 924 resistor load inverter voltage transfer characteristics, VTC, A, NMOSFET with load resistor RL and load parasitic capacitance C, B, determination of VTC by superimposing the load line, linear current voltage ohmic characteristics of the resistor, on NMOSFET output characteristics, C, VTC showing output voltage as a function of input voltage. The 5 key points on the VTC are logic high, VOH, logic low, vol, unity gain points. VIL and VIH, and logic threshold where input equals output, VM. Two other key points are the unity gain points, VIL and VIH. The significance of these points is that if the input voltage is between them, the change of the input is amplified and we get a larger change of the output voltage. Outside of this operating range, the change of the input voltage is attenuated. Clearly, any noise voltage which puts the input voltage between VIL and VIH would be amplified, and lead to a potential problem with the circuit operation. Let us see how to go about determining the VTC. From the circuit in Fig 924a, we see that in the output loop from the power supply to ground, the current through the resistor load is the same as the drain current of the MOSFET. The power supply voltage is equal to the voltage drop across the resistor plus the drain to source voltage. To determine the VTC, we superimpose the load line of the load element, in this case a straight line for an ohmic resistor, on the output characteristics of the MOSFET, Fig 924b. This is similar to our load line discussion in section 6.1.1. The load line goes through VDD on the voltage axis because when the current in the output loop is 0, there is no voltage drop across the resistor and all the voltage appears across the MOSFET. On the current axis, the load line goes through VDD/RL because when the voltage across the MOSFET is 0, the voltage across the resistor must be VDD. As we change the input bias, VEN, we change the gate bias on the MOSFET, and thus in Fig 924b, we go from one constant VG curve to the next. At each input bias, and a corresponding constant VG curve, the intersection of the load line with that curve tells us what the drain bias VD is, which is the same as the output voltage. This is because at the point of intersection, we satisfy the condition that for the DC case where the capacitor does not play any role, the current through the resistor is the same as the MOSFET current. Later on, we shall see that in the AC case when the logic gates are switched, we need to worry about the displacement current through the capacitor when it is charged or discharged. It can be clearly seen from Fig 924c that as the input voltage, or VG, changes from low to high, the output voltage decreases from a high of VDD to a low of VOL. We can solve for any point on this VTC curve analytically simply by recognizing whether the MOSFET is in the linear region or in saturation, using the corresponding drain current expression EQ 649, or 653, and setting it equal to the resistor current. As an illustration, suppose we want to determine the logic 0 level, VOL. This occurs when the input VG is high and the output VD is low, putting the transistor in the linear region. Using EQ 649, we can write. Since in the DC case the current through the MOSFET is the same as that through the resistor, we can solve for VOL if we know RL and the MOSFET parameters. Alternatively, we can design the value of RL to achieve a certain VOL. What might dictate the choice of RL we shall see later in this section that for many applications we use two of these inverters in a cross-coupled manner to form a bistable flip-flop. The output of one inverter is fed back to the input of the other, and vice versa. Clearly, the VOL must be designed to be significantly less than the threshold voltage of the MOSFET. Otherwise, neither MOSFET will be fully turned off, and the flip-flop will not function properly. Similarly, all the other points on the VTC can be determined analytically by using the appropriate MOSFET drain current expression, and setting it equal to the current through the resistor. We can make some general observations from this analysis. We want the transition region of the VTC, between VIL and VIH, to be as steep, i.e., high gain, as possible, and the transition should be around VDD/2. High gain guarantees a high-speed transition from one logic state to the other. It is necessary to increase the load resistance to increase this gain in the transition region. The transition around VDD/2 guarantees high noise immunity or margin for both logic 1 and logic 0 levels. To appreciate the importance of noise immunity, we must recognize that in combinatorial or sequential digital circuits, the output of one inverter or logic gate is often fed into the input of the next stage. Noise immunity is a measure of how much noise voltage the circuit can tolerate at the input, and still have the digital outputs be at the correct logic level in the subsequent stages. For example, in Fig 924C, if the input is nominally at 0, the output should be high, logic 1. If this is fed into another inverter stage, its output should be low, and so on. If a noise spike causes the input of the first stage to go above Vm, the output voltage decreases sufficiently to potentially create errors in the digital levels in subsequent stages. Having a symmetric transition of the VTC around VDD/2 ensures that the noise margin is high for both logic levels. One problem with the resistor load inverter is that the vol is low, but not 0. This, coupled with the fact that the load element is a passive resistor that cannot be turned off, causes high standby power dissipation in the circuit. These problems are addressed by the complementary metal oxide semiconductor structure described next. We can determine the VTC for the CMOS case exactly as for the resistor load, although the math is somewhat more messy, Fig 925. As mentioned previously, for an input voltage VEN, the VG of the N-channel MOSFET is VEN, but that of the P-channel metal oxide semiconductor field effect transistor is V input, VDD. Similarly, if the output voltage is output voltage, the drain voltage of the N-channel metal oxide semiconductor field effect transistor is V output, but that of the P metal oxide semiconductor is V output, VDD. The load element now is not a simple resistor with a linear current voltage relationship, but instead is the P-channel MOSFET device whose load line is a set of drain current, drain voltage output characteristics, Fig 925b. The VOUT can be determined as a function of the VEN by recognizing whether the N-channel MOSFET and the P-channel MOSFET are in the linear or saturation region of their characteristics, and using the appropriate current expressions. At each point, we would set the N-channel metal oxide semiconductor field effect transistor drain current equal to the P-channel metal oxide semiconductor field effect transistor drain current. As in the case of the resistive load, there are 5 key points on the VTC, Fig 925c. They are logic 1 equal to VDD, logic 0 equal to 0, logic threshold Vm where VEN equal VOUT, and the 2 unity gain points, VIH and VIL. In region I in Fig 925c, the N-channel MOSFET is off, and VOUT equal VDD. Similarly, in region V, the P-channel MOSFET is off, and output voltage equal 0. We can illustrate the calculation in region 2, where the N-channel MOSFET is in saturation and the P-channel MOSFET is in the linear region. In this case, we must use EQ 653, for the saturation drain current of the N-channel MOSFET. We are considering the long channel case. On the other hand, we must use EQ 649, for the P-channel MOSFET in the linear region. Figure 925 Complementary metal oxide semiconductor inverter voltage transfer characteristics, A. N-channel MOSFET with P-channel MOSFET load and load parasitic capacitance, C. B. Determination of VTC by superimposing load line, output characteristics of P-channel MOSFET shown as dotted line, on N-channel MOSFET output characteristics, C. VTC showing output voltage as a function of input voltage. The 5 key points on the VTC are logic high, VOH, logic low, VOL, unity gain points, VIL and VIH, and logic threshold where input equals output, VM, D, switching current from VDD to ground when the input voltage is in a range where both the N-channel MOSFET and the P-channel MOSFET are on. Here VTN and VTP are the N and P-channel threshold voltages. In the DC case, since the output load capacitor does not play a role, the drain current through the P-channel MOSFET device must be equal in magnitude to that through the N-channel MOSFET. However, for the AC case, we need to consider the displacement current through the capacitor. Using EQ 653, for the NMOSFET in saturation, and EQ 649, for the P-channel MOSFET in the linear region. From EQ 95b, we can get an analytical relation between the input and output voltages valid in region 2. We can get similar relationships in the other regions of the VTC. Region 4 is very similar to region 2 in Fig 925C, except that now the NMOS is in the linear regime, while the P-channel MOSFET is in saturation. In region 3, both the N-channel MOSFET and the P-channel MOSFET are in saturation. Since the output impedance of a MOSFET is very high, this is tantamount to a semi-infinite load resistor, thereby resulting in a very steep transition region. That is why a CMOS inverter switches faster than the resistor load case. The CMOS inverter is also preferable because in either logic state, regions I or V, either the N-channel MOSFET or the P-channel MOSFET is off, and the standby power dissipation is very low. In fact, the current in either logic state corresponds to the very low source drain diode leakage. We want the transition region, region 3, to be at VDD divided by 2 from the point of view of symmetry and noise immunity. Once again, by setting the NMOS-FET ID equal to that of the PMOS-FET, it can be shown that the transition occurs at where we can design VEN to be at VDD divided by 2 by choosing VTN equal, VTP and X equal 1. Since the effective electron mobility in the channel of a silicon metal oxide semiconductor field effect transistor is roughly twice that of the hole mobility, we must design complementary metal oxide semiconductor circuits to have a Z/L, P equal to, Z/L, and to achieve the condition X equal 1. We can combine such CMOS inverters to form other logic gates for combinatorial circuits such as NOR gates and NAND gates, Fig 926. The truth tables for these gates are shown in Fig 927. By applying combinations of logic high or logic low to inputs A and B, we get the output states corresponding to the truth tables. The synthesis of logic circuits corresponding to these truth tables can be done using Boolean algebra and De Morgan's laws. The upshot of these laws is that any logic circuit can be made using inverters in conjunction with either NAND gates or NOR gates. Which would be preferable from a device physics point of view? We see from Fig 926, that in the NOR gate the P-channel MOSFET devices T3 and T4 are in series, while for the NAND it is the N-channel MOSFETs, T1 and T2. Since the electron channel mobilities are twice hole mobilities, we would obviously prefer N-channel MOSFETs. Therefore, the preferred choice is NAND, along with inverters. Figure 926 logic gates and CMOS implementation of A. NOR gate, B. NAND gate. We can also estimate the power dissipation in the inverter circuit. We already know that the standby power dissipation is very small, being governed by the off-state leakage current of either the NMOS-FET or the PMOS-FET, depending on the logic state. This leakage current depends on the source and drain diode leakage currents, or if the VT is low, on the subthreshold leakage of the MOSFET that is turned off, see section 6.5.7. While the inverter is switching, there is also a transient current from the power supply to ground when both the transistors are on, see Fig 925D. This is known as the switching current or the commutator current. The magnitude of this current will clearly depend on the values of VTN and VTP. The higher the magnitudes of the thresholds, the less is the input voltage swing for which both the PMOS-FET and the NMOS-FET will be on while the input voltage is being changed. The commutator current is then less during switching, which is desirable from a reduced power dissipation point of view. However, this reduction of power dissipation by increasing threshold voltages is obtained at the expense of reduced drive current and, therefore, overall speed of the circuit. Figure 927, A, and /NAND logic symbols and truth table, B, or /NOR logic symbols and truth table, C, X or logic symbol and truth table. The speed penalty due to reduction of drive current is because in a digital circuit, while switching between logic states, the MOSFET drive currents must charge and discharge the parasitic capacitors that are inevitably associated with the output node, Fig 925a. There is also some power dissipation involved in charging and discharging load capacitors attached to the output of the inverter. This load capacitance depends mostly on the input gate oxide capacitance of the MOSFETs of the next inverter stage, or logic gate, that this inverter, or logic gate, may be driving, along with some small parasitic capacitances. The input load capacitance of a single inverter is given by gate oxide capacitance per unit area Ci times the device areas. The total load capacitance is then multiplied by a factor that depends on the fan-out of the circuit, which is the number of gates that are being driven in parallel by the inverter, or logic gate. It is necessary to add up the load capacitances for all the inverters or logic gates that are being driven by this inverter stage. The energy expended in charging up the equivalent load capacitor, C, is the integral of the product of the time-dependent voltage times the time-dependent displacement current through the capacitor during the charging cycle. The energy stored in C is then obtained by considering the displacement current, IP, T, equals C dV/dt, through the capacitor. Similarly, during one discharging cycle we get, if the inverter, or gate, is being charged and discharged at a frequency f, we get an active power dissipation. In addition to power dissipation, we are also concerned with the speed of logic circuits. The speed of a gate, such as the one shown in Fig 925, is determined by the propagation delay time Tp. We define the time required for the output to go from the logic high VOH to VOH/2 as TPHL. The converse, to go from logic low vol, equal 0, to VOH/2, is defined as TPLH. We can write down approximate estimates for these times by recognizing that for the output to go from high to low, or logic 1 to 0, the N-channel MOSFET has to discharge the output node toward ground. During this period, the N-channel MOSFET will be in saturation. Assuming a constant saturation current as an approximation, we obtain from EQ 653. This is the decrease of charge on the capacitor divided by the discharging current. Conversely, knowing these times helps us considerably in designing circuits that meet the speed requirements of a design. Of course, for accurate numerical estimates of these propagation time delays or of the power dissipation we need to use computers. A very popular program to do so is the simulation program with integrated circuit emphasis, SPICE. This discussion illustrates that the device physics plays an important role in the design and analysis of such circuits. Semiconductor memories. In addition to logic devices such as microprocessors, integrated circuits depend on semiconductor memories. We can illustrate many CMOS device physics issues by looking at three of the most important types of semiconductor memory cells: the static random access memory, SRAM, the dynamic random access memory, DRAM, and the non-volatile flash memory cell. SRAMs and DRAMs are volatile in the sense that the information is lost if the power supply is removed. For flash memories, however, information is stored indefinitely. For SRAMs, the information is static, meaning that as long as the power supply is on, the information is retained. On the other hand, the information stored in the cells of a DRAM must periodically be refreshed because stored charge representing one of the logic states leaks away rapidly. The refresh time must be short compared with the time needed for stored charge to degrade. The overall organization of all these types of memories is rather similar, and is shown in Fig 928. We will not describe the memory organization in great detail here, but will instead focus on the device physics. Figure 928 Organization of a random access memory, RAM. The memory array consists of memory cells arranged in an orthogonal array. There is one memory cell at the intersection of one row, word line, and one column, bit line. To address a particular memory cell, the n-row addresses are latched in from the n-address pins, and decoded by the two n-row decoders. All the memory cells on the selected row are read by the 2N sense amplifiers. Of those, a cell, 1 bit, or group of cells, byte or word, is selected for transfer to the data output buffers depending on the column addresses that are decoded by the 2N column decoders. Generally, to save pin count on the package, the N column addresses are provided in a multiplexed fashion to the same N address pins as the row addresses, after the row addresses have already been latched in. We need to know the type of cell that is used at the intersection of the rows or word lines, and the columns or bit lines. These memories are all random access in the sense that the cells can be addressed for write or read operations in any order, depending on the row and column addresses provided to the address pins, unlike memories such as hard disks or floppy disks on a computer which can only be addressed sequentially. Generally, the same set of pins is used for both the row and the column addresses, in order to save pin count. This forces us to use what is known as address multiplexing. First, the row addresses are provided at the address pin, and decoded using row decoders. For N row addresses, we can have 2 N rows or word lines. The row decoders then cause the selected word line to go high, so that all the 2 N cells, corresponding to N column addresses, on this word line are accessed for either read or write, through sense amplifiers at the end of the 2 N columns or bit lines. After the appropriate row has been decoded, the appropriate column addresses are provided to the same address pins, and the column decoders are used to select the bit or group of bits, known as byte or word, out of all the 2 N bits on the selected word line. We can either write into or read from the selected bit, or group of bits, using the sense amplifiers, which are basically flip-flops or differential amplifiers. SRAMs. A group of 4 6-transistor CMOS SRAM cells is shown in Fig 929. Each cell is found in this case at the intersection of a row or word line, and a column or bit line, along with its logical complement known as bitline bar. The cell is a flip-flop, consisting of 2 cross-coupled CMOS inverters. Clearly, it is bistable, if the output of one inverter is high, corresponding to the NMOSFET being off, and the PMOSFET on, that high voltage is fed to the input of the other cross-coupled inverter, and the output of the other inverter will be low. This is one logic state, say 1, of the SRAM. Conversely, the other stable state of the flip-flop can be considered to be the other logic state, say 0. Many of the device issues are identical to those described in section 9.5.1 in connection with the VTC of inverters. Figure 929. An array of 4 complementary metal oxide semiconductor static random access memory cells. The bitline and bitline bar, are logical complements of each other. We aim for a symmetric transition from VOH to VOL at VDD/2 with a high gain in the transition region, to improve noise immunity and speed of convergence of the static random access memory cell. The speed of convergence determines how fast the static random access memory flip-flop latches into one stable logic state or the other. The cells are accessed through 2 access transistors whose gates are controlled by the word line. That is why this is called a 6-transistor cell. Other SRAM cells use load resistors in the inverters, rather than P-channel MOSFET, leading to a 4-transistor, 2-resistor cell. As discussed in section 9.5.1, the CMOS cell has superior performance, but at the expense of occupying more area. Unless the row decoders cause a particular word line to go high, the SRAM cells on that word line are electrically isolated. By selecting a particular word line, the access transistors on that row are turned on and act as logic transmission gates between the output nodes of the SRAM cell and the bitline and its complement, the bitline bar. During a read operation, the bitline and its complement are both pre-charged to the same voltage. Once the access transistors are turned on, a small voltage differential develops between bitline and bitline bar because the output nodes of the SRAM are at different voltages, 0 and VDD. The voltage differential that is established is due to a charge redistribution that occurs between the parasitic capacitance associated with the output nodes of the SRAM and the bitline capacitance. This voltage difference is amplified by the sense amplifiers. As mentioned previously, the sense amplifiers are differential amplifiers, very similar in configuration to the SRAM flip-flop cell itself. The bitline and bitline bar, complement of the bitline, are fed to the two inputs of the sense amplifier, and the voltage differential is amplified until the voltage separation is VDD. Dynamic random access memories. The dynamic random access memory cell structure is shown in Fig 930. The information is stored as charge on a metal oxide semiconductor capacitor, which is connected to the bitline through a switch which is an MOS pass transistor, the gate of which is controlled by the word line. There is one such cell at each intersection of the orthogonal array of word lines and bit lines, exactly as for static random access memories. When the word line voltage becomes higher than the threshold voltage of the pass transistor, MOSFET between the bitline and the storage capacitor, the channel is turned on, and connects the bitline to the MOS storage capacitor. The gate of this capacitor, or capacitor plate, is permanently connected to the power supply voltage VDD, thereby creating a potential well under it which tends to be full of inversion electrons for a p-type substrate, Fig 931a. We apply either 0V to the bitline, generally corresponding to logic 0, or VDD, corresponding to logic 1, and the appropriate voltage appears as the substrate potential of the MOS capacitor. For a stored 0 in the cell, the potential well that is created under the MOS capacitor by the plate voltage is full of inversion charge, Fig 931b, c. When the word line voltage is turned low such that the MOS pass transistor is turned off, the inversion charge under the storage capacitor stays the same. This is the stable state of the capacitor. Figure 931 transistor, 1 capacitor dynamic random access memory cell equivalent circuit. The storage metal oxide semiconductor capacitor is connected to the bitline through the pass transistor, MOSFET switch, whose gate is controlled by the word line. On the other hand, if a positive voltage, VDD, is applied to the bitline, it draws out the inversion electrons through the pass transistor, Fig 931d, E. When the pass transistor is cut off, we end up with an empty potential well under the metal oxide semiconductor capacitor plate. Over a period of time, the potential well tends to be filled up by minority carrier electrons that are constantly created by thermal generation recombination in the substrate and are collected under the charged metal oxide semiconductor capacitor plate. Hence, the logic 1 degrades towards the logic 0. That is why a DRAM is considered to be dynamic unlike an static random access memory. It is necessary to periodically restore the logic levels or refresh the stored information. There are interesting device physics issues regarding the pass transistor. This is like the access transistor in the static random access memory, or a logic transmission gate. We see that in this MOSFET, neither the source nor the drain is permanently grounded. In fact, which side acts as the source and which as the drain depends on the circuit operation. When we are writing a logic 1 into the cell, the bitline voltage is held high, equal VDD. As this voltage is written into the cell, it is as if the source of the pass transistor gets charged up to VDD. Another way of looking at this is that with respect to the source, the substrate bias of the pass transistor is VDD. The body effect of the metal oxide semiconductor field effect transistor, section 6.5.6, causes its threshold voltage to increase. This is very important because for the pass transistor to operate as a transmission gate it is necessary that it be in the linear regime throughout, and not get into saturation, with a concomitant voltage drop across the pinch-off region. Hence, the gate or the word line voltage must be held at VDD, which is the final voltage of the source/drains, plus the threshold voltage of the metal oxide semiconductor field effect transistor, taking body effect into account. It is also important to make sure that the leakage of the pass transistor is low enough to satisfy refresh requirements of the dynamic random access memory. Figure 931 Dynamic random access memory cell structure and cell operation. A. Cell structure corresponding to equivalent circuit of Fig 930. B. E. Potentials under bitline, pass transistor channel and storage capacitor during write 0, store 0, write 1 and store 1 operations. It shows that the logic state 0 corresponds to a filled potential well, stable state, while the logic state 1 corresponds to an empty potential well, unstable state, that is filled up over time by minority carriers generated in the substrate and leakage through the pass transistor. Not only must the source/drain diodes be low leakage, but the threshold voltage and the subthreshold slope must be optimized such that subthreshold leakage for the grounded word line case is low enough. The stored charge difference between the two logic states can be determined by looking at the capacitance voltage, CV, characteristics of the metal oxide semiconductor capacitor, Fig 932. For a stored one, essentially there is a substrate bias applied to the metal oxide semiconductor capacitor, which raises its threshold voltage due to the body effect, section 6.5.6. Hence, the capacitance voltage characteristics shift to the right for a stored one. Since the MOS capacitance is not a fixed capacitance, but is voltage dependent, we saw earlier that it must be defined in a differential form EQ. 634a. Alternatively, we can write down the stored charge under the capacitor as. This is simply the area under the capacitance voltage curve. The charge differential that distinguishes the logic 1 and the logic 0 is the difference of areas under the capacitance voltage curves in the two cases, Fig 932. When reading the cell, the pass transistor is turned on, and the metal oxide semiconductor storage capacitor charge is dumped on the bit line capacitance CB, pre-charged to VB, typically equal VDD. The swing of the bit line voltage will clearly depend on the voltage VC stored in the storage cell capacitance CC. As in the case of the SRAM, the change of the bit line voltage depends on the capacitance ratio between the bit line and the cell. Figure 932 capacitance voltage characteristics of dynamic random access memory metal oxide semiconductor capacitor in stored 0 and stored 1 states. The difference of area under the capacitance voltage curves shown by hatch-marked pattern reflects the charge differential between the two states. Figure 933 equivalent circuit showing charge redistribution between cell capacitance, CC, and bit line capacitance, CB, on one side, versus dummy cell, CD, and bit line capacitance, CB, on other. To do differential sensing in the case of dynamic random access memories, we do not use 2 bit lines per cell as for static random access memories. Instead, we compare the bit line voltage for the selected cell with a reference bit line voltage to which is connected a dummy cell whose metal oxide semiconductor capacitance, CD, is roughly half that of the actual cell capacitance, CC. Typical values of CB, CC, and CD in a dynamic random access memory are 800 FF, 50 FF, and 20 FF, respectively. The voltage differential that is applied to the sense amplifier then becomes, Fig 933. Putting the cell voltage VC equal to 0V or 5V, and typical, acceptable bit line to cell capacitance ratios CB/CC, equal 15 to 20, in EQ. 913b, we get different polarities of the differential voltage of the order of 100 mV for logic 1 and logic 0, respectively, which can be detected by sense amplifiers. From EQ 913b, it can be seen that for much higher bit line to cell capacitance ratios, the swing of the bit line voltage will be negligible, regardless of the cell voltage. The minimum required cell capacitance CC is about 50 FF, governed by so-called soft errors. Dynamic random access memories, like everything else on Earth, are constantly being bombarded by cosmic rays, and high-energy alpha particles can create electron-hole pairs in semiconductors. A typical collected charge due to one of these events is about 100 Fc. This spurious charge can be neglected if the cell capacitance is 50 FF and 5V is applied to the cell, for which the stored charge is roughly 250 Fc. The dynamic random access memory cell then becomes immune to typical alpha particle hits. Maintaining a cell capacitance of 50 FF as the cell dimensions are reduced from one generation of dynamic random access memory to the next is a tremendous technological challenge. One way to look at this problem is shown in Fig 934. The challenge is to store more charge per unit area on the planar surface, as, of the silicon substrate. Approximating the Mohs capacitance as a fixed, voltage-independent capacitor, we can write the stored charge Q as where G is the permittivity of the dielectric, D is its thickness, and AC is the capacitor area. As shown in Fig 934, the historical way of achieving the desired capacitance has been to scale the dielectric thickness, D. Figure 934 various approaches, past, present, and future, of achieving higher dynamic random access memory cell capacitance and charge storage density without increasing cell size. As equal area on wafer taken by capacitor, AC equal area of capacitor. For a planar capacitor AC equal as, however, for non-planar structures AC is greater than Asia. C equal ACP/D is the capacitance, and Q equal CV is the total stored charge in a fixed, voltage-independent capacitor. But that runs into the problems discussed in section 6.4.7. Another approach, which is being taken currently, is to use fabrication schemes to increase the area devoted to the metal oxide semiconductor storage capacitor, AC, even as we reduce the planar surface area on the wafer, as used for making the storage capacitance. Obviously, this can be done by moving away from a purely planar structure, and exploiting the third dimension. We can go down into the silicon by digging trenches in the substrate with reactive ion etching and forming a trench storage capacitor on the sidewalls of the trench, Fig 935a. Alternatively, we can go up from the substrate by stacking multiple layers of capacitor electrodes to increase the stacked capacitor area, Fig 935b. Other tricks that have been tried are to purposely create a rough polysilicon surface on the capacitor plates to increase the surface area. In the future, alternative materials may be used. For example, the ferroelectrics have much higher dielectric constant than silicon dioxides and offer larger capacitance without increasing area or reducing thickness. Promising materials include barium strontium titanate and zirconium oxide. Flash memories. Another interesting metal oxide semiconductor device is the flash memory, which is the most important type of nonvolatile memory. The memory cell structure is shown in Fig 936. It is very simple and compact, and looks just like a MOSFET, except that it has two gate electrodes, one on top of the other. The top electrode is the one that we have direct electrical access to, and is known as the control gate. Figure 935 increasing cell capacitance by exploiting the vertical dimension. A. Trench capacitors involve etching a trench in the substrate so that the larger area on the sidewalls can be used to increase capacitance. B. Stacked capacitors go up rather than down as in trenches, and increase capacitor area by using multiple polysilicon capacitor plates or fins, as well as by exploiting the topography of the cell surface. Figure 936 flash memory cell structure. A. Cell structure shown along the channel length showing the control gate, word line, floating gate below it, the source and the drain, bit line. B. View of cell along the width of the metal oxide semiconductor field effect transistor. The various coupling capacitors to the floating gate are shown. Below that we have a so-called floating gate that is capacitively coupled to the control gate and the underlying silicon. The capacitive coupling of the floating gate to the various terminals is illustrated in Fig 936 in terms of the various coupling capacitance components. The floating gate and the control gate are separated by a stacked oxide nitride oxide dielectric in typical flash devices. The capacitance between these two gates is called CONO because of the oxide nitride oxide makeup of the dielectric stack. The total capacitance CTOT is the sum of all the parallel components shown in Fig 936. Where CTOX is the floating gate to channel capacitance through the tunnel oxide, CFLD is the floating gate to substrate capacitance in the Locos field oxide region, and CSRC and CDRN are the gate to source/drain overlap. Capacitances. Since it is isolated by the surrounding dielectrics, the charge on the floating gate QFG is not changed by moderate changes of the terminal biases. We assume that the substrate bias is fixed, and hence ignore the contributions from CTOX and CFLD, which couple the floating gate to the substrate. The floating gate voltage can be indirectly determined by the various terminal voltages, in terms of the gate, drain, and source coupling ratios as defined in EQ 917. Where the basic cell operation involves putting charge on the floating gate or removing it, in order to program the MOSFET to have two different threshold voltages, corresponding to two logic levels. We can think of the stored charge on the floating gate to be like the fixed oxide charge in the threshold voltage expression EQ 638. If many electrons are stored in the floating gate, the threshold voltage of an NMOSFET is high, the cell is considered to have been programmed to exhibit the logic state 0. On the contrary, if electrons have been removed from the floating gate, the cell is considered to have been erased into a low threshold voltage state or logic 1. How do we go about transferring charges into and out of the floating gate? To program the cell, we can use channel hot carrier effects that we discussed in section 6.5.9. We apply a high field to both the drain, bit line, and floating gate, word line, such that the MOSFET is in saturation. It was discussed in section 6.5.9 that the high longitudinal electric field in the Pinch-Off region accelerates electrons toward the drain and makes them energetic, hot. We maximize such hot carrier effects near the drain pinch-off region in a flash device by making the drain junction somewhat shallower than the source junction, Fig 937a. This can be achieved by a separate higher energy source implant that is masked in the drain region. If the kinetic energy of electrons is high enough, a few can become hot enough to be scattered into the floating gate. They must surmount the 3.1 electron volts energy barrier that exists between the conduction band of silicon and that of silicon dioxide, or hot electrons can tunnel through the oxide, Fig 937b. Once they get into the floating gate, electrons become trapped in the 3.1 electron volt potential well between the floating polysilicon gate and the oxides on either side. This barrier is extremely high for a trapped, low kinetic energy, electron. Therefore the trapped electrons essentially stay in the floating gate forever, unless the cell is intentionally erased. That is why a flash memory is non-volatile. To erase the cell, we use Fowler-Nordheim tunneling between the floating gate and the source in the overlap region, Fig 938a. A high positive voltage, say 12V, is applied to the source with the control gate grounded. Figure 937 hot carrier programming of the flash cell. A. Flash memory cell structure with typical biases required for writing into the cell. The channel of the metal oxide semiconductor field effect transistor is pinched off in saturation. B. Band diagram along a vertical line in the middle of metal oxide semiconductor field effect transistor channel showing hot electrons in the channel being injected across the gate oxide and getting trapped in the floating gate. Figure 938 Fowler-Nordheim tunneling erasure. A. Flash memory cell structure with typical biases required for erasing the cell. B. Band diagram as a function of depth in the gate/source overlap region of the metal oxide semiconductor field effect transistor showing quantum mechanical tunneling of carriers from the floating gate into the oxide, and subsequent drift to the source. The polarity of the field is such that electrons tunnel from the floating gate into the source region, through the oxide barrier, section 6.4.7. The band diagram, along a vertical line in this overlap region, during the operation is shown in Fig 938b. Interestingly, in a flash device we make use of two effects that are considered to be problems in regular MOS devices, hot carrier effects and Fowler-Nordheim tunneling. Figure 939 drain, bit line, current versus control gate, word line, voltage transfer characteristics of the metal oxide semiconductor field effect transistor in a flash cell. If the cell is programmed to a high threshold voltage, logic 0, and a red voltage is applied to the word line that is below this threshold voltage, the metal oxide semiconductor field effect transistor does not conduct, and there is negligible bit line current. On the other hand, if the cell had been erased to a low threshold voltage state, logic 1, the metal oxide semiconductor field effect transistor is turned on, and there is significant bit line current. During the read operation, we apply a moderate voltage, 1V, to the bit line, drain of the MOSFET, and a word line, control gate, voltage VCG that causes the capacitively coupled floating gate voltage to be between that of the high threshold voltage and the low threshold voltage state of the programmed flash memory cell, Fig 939. There will be negligible drain current flow in the bit line, drain, for the high threshold voltage case because the gate voltage is less than the threshold voltage. We will then interpret the selected cell as being in state 0. For the low threshold voltage case, since the applied gate voltage is higher than the threshold voltage of the cell, there will be drain current flow in the bit line, drain, and this can be interpreted as state 1. The read operation can be understood by looking at the transfer characteristics of the metal oxide semiconductor field effect transistor in the programmed and erased states, Fig 939. After the preceding discussions of rather dramatic fabrication steps in monolithic circuit technology, the processes of attaching leads and packaging the devices could seem rather mundane. Such an impression would be far from accurate, however, since the techniques discussed in this section are crucial to the overall fabrication process. In fact, the handling and packaging of individual circuits can be the most critical steps of all from the viewpoints of cost and reliability. The individual integrated circuit chip must be connected properly to outside leads and packaged in a way that is convenient for use in a larger circuit or system. Since the devices are handled individually once they are separated from the wafer, bonding and packaging are expensive processes. Considerable work has been done to reduce the steps required in bonding. We shall discuss the most straightforward technique first, which involves bonding individual leads from the contact pads on the circuit to terminals in the package. Then we shall consider two important methods for making all bonds simultaneously. Finally, we shall discuss a few typical packaging methods for integrated circuits. Testing. After the wafer of monolithic circuits has been processed and the final metallization pattern defined, it is placed in a holder under a microscope and is aligned for testing by a multiple point probe, Fig 940. The probe contacts the various pads on an individual circuit, and a series of tests are made of the electrical properties of the device. The various tests are programmed to be made automatically in a very short time. These tests may take only milliseconds for a simple circuit, to several seconds for a complex ULSI chip. The information from these tests is fed into a computer, which compares the results with information stored in its memory, and a decision is made regarding the acceptability of the circuit. If there is some defect so that the circuit falls below specifications, the computer remembers that chip must be discarded. The probe automatically steps the prescribed distance to the next circuit on the wafer and repeats the process. After all of the circuits have been tested and the substandard ones noted, the wafer is removed from the testing machine, sawed between the circuits, and broken apart, Fig 941. Then each die that passed the test is picked up and placed in the package. In the testing process, information from tests on each die can be stored to facilitate analysis of the rejected circuits or to evaluate the fabrication process for possible changes. Wire bonding. The earliest method used for making contacts from the monolithic chip to the package was the bonding of fine gold wires. Later techniques expanded wire bonding to include aluminum wires and several types of bonding processes. Here we shall outline only a few of the most important aspects of wire bonding. If the chip is to be wire bonded, it is first mounted solidly on a metal lead frame or on a metallized region in the package. In this process a thin layer of gold, perhaps combined with germanium or other elements to improve the metallurgy of the bond, is placed between the bottom of the chip and the substrate. Heat and a slight scrubbing motion are applied, forming an alloyed bond which holds the chip firmly to the substrate. This process is called die bonding. Generally, die bonding is done by a robotic arm that picks up each die, orients it, and places it for bonding. Once the chip is mounted, the interconnecting wires are attached from the various contact pads to posts on the package, Fig 942. In gold wire bonding, a spool of fine gold wire, about 0.007 to 0.0002 inch diameter, is mounted in a lead bonder apparatus, and the wire is fed through a glass or tungsten carbide capillary, Fig 943a. A hydrogen gas flame jet is swept past the wire to form a ball on the end. In thermocompression bonding, the chip, or in some cases the capillary, is heated to about 360 degrees Celsius, and the capillary is brought down over the contact pad. When pressure is exerted by the capillary on the ball, a bond is formed between the gold ball and the aluminum pad, Fig 943b. Then the capillary is raised and moved to a post on the package. The capillary is brought down again, and the combination of force and temperature bonds the wire to the post. After raising the capillary again, the hydrogen flame is swept past, forming a new ball, Fig 943c, then the process is repeated for the other pads on the chip. Figure 940. Automated probing of devices. A. High-speed testing of integrated circuits is done using probe cards having a rigidly fixed array of probes that corresponds to the bond pad pattern on the integrated circuit to be tested. Many electrical signals are provided or measured by the automated tester at the various pins. After one chip is tested, the tester mechanically moves the wafer to the next die location, B. Array of aluminum bond pads near the chip periphery, some showing probe marks. The space between the arrays of bond pads is the scribe line along which the wafer will be sawed into individual chips after testing. 2004 Micron Technology, Incorporated. Figure 941. Sawing of a wafer along scribe lines. After the wafer is tested, the known good dies are inked or identified. The wafer is then sawed into individual dies for subsequent packaging. 2004 Micron Technology, Incorporated. Figure 942. Attachment of leads from the aluminum pads on the periphery of the chip to posts on the package. 2004 Micron Technology, Incorporated. There are many variations in this basic method. For example, the substrate heating can be eliminated by ultrasonic bonding. In this method, a tungsten carbide capillary is held by a tool connected to an ultrasonic transducer. When it is in contact with a pad or a post, the wire is vibrated under pressure to form a bond. Other variations include techniques for automatically removing the tail, which is left on the post in Fig 943c. When the bond to the chip is made by exerting pressure on a ball at the end of the gold wire, it is called a ball bond or a nail head bond, because of the shape of the deformed ball after the bond is made, Fig 944a. Aluminum wire can be used in ultrasonic bonding. It has several advantages over gold, including the absence of possible metallurgical problems in bonds between gold and aluminum pads. When aluminum wire is used, the flame-off step is replaced by cutting or breaking the wire at appropriate points in the process. In forming a bond, the wire is bent under the edge of a wedge-shaped bonding tool, Fig 943d. The tool then applies pressure and ultrasonic vibration, forming the bond, Fig 943e and f. The resulting flat bond, formed by the bent wire wedged between the tool and the bonding surface, is called a wedge bond. A close-up view of ball and wedge bonds is given in Fig 944. Figure 943. Wire bonding techniques. A. Capillary positioned over one of the contact pads for a ball, nail head, bond. B. Pressure exerted to bond the wire to the pad. C. Post bond and flame-off. D. Wedge bonding tool. E. Pressure and ultrasonic energy applied. F. Post bond completed and wire broken or cut for next bond. Figure 944. Scanning electron micrographs of a ball bond, A, and a wedge bond, B. 2004 Micron Technology, Incorporated. Flip chip techniques. The time consumed in bonding wires individually to each pad on the chip can be overcome by several methods of simultaneous bonding. The flip chip approach is typical of these methods. Relatively thick metal is deposited on the contact pads before the devices are separated from the wafer. After separation, the deposited metal is used to contact a matching metallized pattern on the package substrate. In the flip chip method, bumps of solder or special metal alloys are deposited on each contact pad. These metal bumps can be distributed over the die, Fig 945. After separation from the wafer, each chip is turned upside down, and the bumps are properly aligned with the metallization pattern on the substrate. At this point, ultrasonic bonding or solder attaches each bump to its corresponding connector on the substrate. An obvious advantage of this method is that all connections are made simultaneously. Disadvantages include the fact that the bonds are made under the chip and therefore cannot be inspected visually. Furthermore, it is necessary to heat and/or exert pressure on the chip. Packaging. The final step in integrated circuit fabrication is packaging the device in a suitable medium that can protect it from the environment of its intended application. In most cases this means the surface of the device must be isolated from moisture and contaminants, and the bonds and other elements must be protected from corrosion and mechanical shock. The problems of surface protection are greatly minimized by modern passivation techniques, but it is still necessary to provide some protection in the packaging. In every case, the choice of package type must be made within the requirements of the application and cost considerations. There are many techniques for encapsulating devices, and the various methods are constantly refined and changed. Here we shall consider just a few general methods for the purpose of illustration. Figure 945 Flip chip bonding. The PowerPC chip has metallized bumps distributed over the surface instead of contact pads around the periphery. These bumps are aligned with the interconnection pattern on the package and bonded simultaneously. Photograph courtesy of IBM Corp. In the early days of IC technology, all devices were packaged in metal headers. In this method the device is alloyed to the surface of the header, wire bonds are made to the header posts, and a metal lid is welded over the device and wiring. Although this method has several drawbacks, it does provide complete sealing of the unit from the outside environment. This is often called a hermetically sealed device. After the chip is mounted on the header and bonds are made to the posts, the header cap can be welded shut in a controlled environment, for example, an inert gas, which maintains the device in a prescribed atmosphere. Integrated circuits are now mounted in packages with many output leads, Fig 946. In one version the chip is mounted on a stamped metal lead frame and wire bonding is done between the chip and the leads. The package is formed by applying a ceramic or plastic case and trimming away the unwanted parts of the lead frame. Broadly speaking, packages can be through-hole mount that involve inserting the package pins through holes on the printed circuit board, PCB. Before soldering, or surface mount type where the leads do not pass through holes in the PCB. Instead, surface-mounted package leads are aligned to electrical contacts on the PCB, and are connected simultaneously by solder reflow. Most packages can be made using ceramic or plastic, which is cheaper. The integrated circuits are hermetically sealed for protection from the environment. The pins can be on one side, single inline or zigzag pattern of leads, two sides, dual inline package or dip, or four sides of the package, quad package, Fig 946. More advanced packages have leads distributed over a large portion of the surface of the package as in through-hole mounted pin grid arrays, PGAs, Fig 947, or surface-mounted ball grid arrays, BGAs, Fig 948. By not restricting the leads to the edges of the package, the pin count can be increased dramatically, which is very attractive for advanced ULSI in which a large number of electrical leads must be accessed. Figure 946 Various types of packaging for ICS. Packages can be through-hole mount or surface mount type, and be made out of plastic or ceramic. The pins can be on one side, SIP, two sides, DIP, or four sides, quad, of the package, or distributed over the surface of the package, PGAs or BGAs. Figure 947 Ceramic Column Grid Array, CCGA. This advanced ceramic package is a type of pin grid array made up of several hundred metal columns. Several ICS with metallized solder bumps on them as in Fig 945 can be flip chip bonded on the back of this package, making this a multi-chip module, MCM. Photograph courtesy of IBM. Figure 948 ball grid array. In this package, the integrated circuit in the middle is wire bonded to electrical connections on the package. The package itself has an array of solder balls on the top, which can be properly aligned and surface mount connected simultaneously to electrical sockets on a PCB using solder reflow. Photograph courtesy of IBM. Since a sizable fraction of the cost of an integrated circuit is due to bonding and packaging, there have been a number of innovations for automating the process. These include the use of film reels that contain the metal contact pattern onto which the chips can be bonded. The film can then be fed into packaging equipment, where the position registration capabilities of a film reel can be used for automated handling. This process, called tape automated bonding, TAB, is particularly useful in mounting several chips on a large ceramic substrate having multilevel interconnection patterns, called a multi-chip module. Summary. 9.1 The progress of integrated circuits can be characterized by an exponential increase in the transistor count and a corresponding decrease in feature size with time, Moore's law. The economics are driven by device scaling and batch processing. 9.2 The dominant integrated circuit technology is digital complementary metal oxide semiconductor, which is the basis of logic circuits, microprocessors, memories, dynamic random access memories, static random access memories, and NVM, and application-specific integrated circuits, ASICs.